and running. But before that, we'll probably head into a bunch of basics, and then we'll probably jump in, and I'll probably tell you the cycle, what we're probably going to do. Instead of just taking the malwares and just, playing around with, we'll probably understand what actually is happening in the industry today. Uh, why should we probably understand the tricks of the trade? Okay. And why should we follow an approach that is actually some sort of meaningful approach, but also yields you a lot of better results when you practice it? So I'll just run through a couple of slides, and then I'll set the context for you to understand what we are doing. And then we'll probably use a mix of tools and manual analysis and a bunch of interesting stuff. So everybody who would have got my email would have the machines that you see here. This machine, sorry, on your left here, right? So this is your REM Nux machine, okay? This is the machine that you would probably be using. Don't worry about the machine on the right. I wanted to show you some advanced techniques. So you will be doing, and then we'll put a pause, and then you'll start watching, and then you'll probably be doing and watching, so that, because to cover the entire malware analysis in 2 hours is like a Herculean task, but this will give you a big heads up towards where you're heading. Okay. Now, whatever sample we are probably doing are all the latest samples that was probably observed during the COVID phase. These were all, one couple of them are very simple. One sample is pretty interesting and easy, but the other two, the other sample is pretty complex. So I thought I'll show you how to do it. And you can also probably just interact with me. I'll ask you questions. So I just wanted to try out something new where you do it, and then when I do it, I make you do the moves. I'm just your mouse pointer and you're the actual user. Okay. So I hope you guys have got this machine up and running. So we have two components. Okay. One is we're going to probably look at a doc malware. Okay. And second, I'm going to probably talk about something where you'll use memory forensics. Okay. An introduction to memory forensics. That's the second part probably that we will cover. And so we'll probably be solving two samples. And if we probably have time, we'll do one traffic analysis exercise where we will extract some details from the traffic analysis. Sweet. So I'll just run through my slides pretty fast. Okay. So I'm just going to show my slides just like this. Not going to put it on full screen more. Okay. So welcome to the class, Hunting Malwares Like a True Digital Detective. I'm Sundar Ramaswami. I had the threat research group. I'm a 2-time TEDx speaker, and ma'am told about all those things. Thank you. I'm also part of Government of India Cyber Surakshit program, where I'm involved with a lot of departments in the government for cybersecurity, and we train people, we talk to people, and all of those things. Okay. Now, what's a goal today? Now, this is like the cycle of chain that we're probably going to follow. Okay. So people have a misconception of malware analysis, saying that you probably take the sample, start running the sample, and then, you play around with it, you get some details, and you're happy about it. Now, that's actually not the right process. Okay. Malware analysis usually involves two goals. Okay. One is to understand what the malware is trying to do. Second, you have to probably find out whom it talks to. What is the infrastructure it is talking to? What exactly is it's doing, and all those details. Okay, and that's the most important part we need to understand. Now, this is actually called as the cycle of infection. Okay, this is our goal, to be honest, for the next 2 hours or 2.5 hours, or what are we probably gonna do. So, what exactly happens? I mean, you probably get an email. So usually email is the 70% mode of entry for a malware that probably kicks in. Okay. So you probably happen to get an email that is targeted to a user or to an organization or something. Okay. Now, we have a portion that we probably have to discuss here. You see this malicious document, right? One can probably ask a question. Okay, why not send the malware? I'll probably talk about malware in the coming slides, but just assume that malware is something bad. Okay, now why have to send that bad thing through a document? Why can't I append it as an attachment, or give it a download link, and then probably somebody clicks on it and they download it and they run it? Now, issue with these things is you have something called as endpoint detection systems, which is called as your antivirus. Kaspersky, McAfee, Bitdefender, all these things, right? Now, all of these things basically work on signature, okay? Now, they'll have a hash. Every file will probably have a hash, unique value created, and that is probably fed to the engine, okay? Now, this is probably like, how do I say that? If you probably go to the railway stations and all these places, right? You'll have a list of convicts that you have to watch out for, pickpockets, right? They'll have their photos. Now, probably they walk in somewhere easily, they'll catch him, but they have to probably go in some disguise to rob or something. That's exactly the point. Now, why a Word document? That's what we're probably going to see. Now, how can a malware sit inside a Word document and then do a bunch of activities, and then it probably going to attack a system and it weakens, okay? Now, this is what we're probably going to see today. Now, there are two ways to approach this. Once it's attacked, you will know what are the IPs and domains it's talking to. You can probably come reverse also and do it. Okay, you can come reverse and then arrive at here, or you can come here and arrive at the issues. Okay, I mean the domains and the IPs. Okay, so for something, there's something called as actually threat hunting. Okay, now what exactly is actually threat hunting? So that like you have to hunt for threats basically. Now that's something called as initial, minimum, procedural, innovative, and leading. Now let's not bother about the other things. Okay, we're probably looking about the innovative aspect, what we are probably going to do. Now, what is this innovative aspect? We are probably going to do a bunch of these things as part of the innovative aspect. We're going to search for patterns in the internet to see if these malwares have occurred in the past or the cyber attacks have occurred in the past. Next is clustering. When you have these data that you've hunted from the internet, when you reverse the sample, when you decode a sample, you'll get a bunch of keywords or information that stands out. Now that also you're probably going to put together, and then probably you are going to cluster it for ML AI, which many of the people will probably be talking about in the upcoming sessions. Now, grouping. This is the most important thing where when you group, when you figure out malwares, what they're doing, right? You probably group their activities, how they run and do a bunch of things to see who is the threat actor, what stands common, what is the style of an actor, what's the style of doing things, and so on. Okay. Now, what's the first thing we'll probably do when we do hunting, right? When you probably start doing hunting, when we even run a malware, right? The things that you probably look for is for the file that we have. So this is probably I'll probably show you it here. Okay, you will have your machine. So you'll have your machine here, right? Now this is basically the file. You'll have a file. This file will have a hash value. Okay. Now when this file probably runs, it's going to talk to a domain name and then IP. So these are the 3 to 4 things that will probably tell you. Network or host artifacts will probably see later. These are the 3 or 4 definitive things that will probably tell you, saying that, okay, now these are the characteristics of a malware, or these are the probable things that is actually standing out. So you'll get to know the threat better. Always don't blindly reverse a sample. Search in the internet and figure out what the sample is trying to do understand what is it, and then you probably try to reverse the sample. It gives you a whole different meaning. So all of you probably would have got this Google Drive's link, right? Now I want you to download something called as International Conference Exercise. There's a file in the Google Drive that I gave you. Can you all just download it? And I'll give you 2 minutes. Can you just download this? Because you have the exercises from starting from here, where we'll see 2 to 3, 4 interesting exercises. And then probably we'll jump to our malware analysis exercise. I want it to be a little interactive. Can some of you unmute when I ask you questions so that it makes, I know it's hard to teach or interact through online, but if you could give me a go, or yes, saying that, okay, sir, I downloaded it or something of that sort, I'll be happy. Did you guys get this link? Did you guys find the file there? You can probably unmute and tell me.
Yes, sir.
Yes,
Awesome.
sir.
Yes, sir.
Brilliant. This yes actually
Yes,
makes
sir.
beautiful. Okay. Now, once you open this, guys, I'll just give you 2 more minutes of a time. Okay, just take your time. Once you probably open this, meanwhile, when you open this, you'll have a bunch of exercises here. Okay, we'll probably go one by one. These are all for our malware exercises. Okay, there's some hidden artifacts that I have, and these are your regular exercises that we'll probably get started. This is a beginning introduction to something that you need to understand. Okay, now can we get started? Everybody is downloaded it. Now what you probably have to do is open this. Okay, once you download it, open this. This is our first exercise. Now this is an exercise that you usually meet up. At least, I mean, you will face this kind of an exercise when you go to an organization. Now threat hunting is essential part of malware analysis. How? Usually when customers, when you probably work in an organization, a customer comes and says, hey, I have a bunch of evidences that you guys failed to catch, or I have a bunch of evidences that you probably need to take a look at it. Okay, can you tell me what stands out, what is interesting in it, and let me know? That's how the customer probably comes to you. Okay, now I'm going to copy paste this open source link. Okay, there's something called a paste bin. Okay, what I'm giving you is actually a paste bin. The paste bin basically contains free open source. It's like a notepad online. Okay, a lot of people put their findings here. Some people put malware code also there, and it's used for a bunch of other useful aspects. Now I want you guys to go through it with me. Can you tell me what are which of these domains are malicious, and what are the strange things you probably guys see here? What are the strange things you guys observe here? I want you guys to unmute and answer, because the workshop has to be interactive, otherwise it'll probably be boring. So there's no right or wrong answer. Any answer when you do an investigation adds a lot of detail and a value. So go ahead.
The first and third link looks normal, but rest of them looks a bit fishy.
Good. First and third link looks normal, is it? Okay, perfect. Rest of the links looks fishy. What do you feel looks fishy? I mean, what your first impressions on it when you probably look at it? What makes you, feel saying that no, dude, this looks bad, like
It's
a
different
stripe?
from the links we see normally.
Okay, this link, right? It looks bad to you. Okay, and what do you feel? This looks in this it actually looks bad. Any other weird things that you observe here? That's a good answer. I like the answer. Any other answers?
Third and fourth are HTTPS links, so they
Oh,
might be secure,
okay,
but I
good.
can't trust that underscore right there.
Okay, perfect. Nice answer. Okay. Now I'll probably break your bubbles now. Okay. All of these are actually malicious. Okay. Now, how do I probably quantify it or qualify it as malicious? Okay. Now, the XYZ, right? So probably when you Google, when you see something strange like this, just do an open source hunting. Okay. Now you just type XYZ malware. Now, usually what happens is this .xyz domains, right? If you see .xyz domains, those are the most abused domains that are actually shown as malware. Okay. If you see XYZ or .top domains, you can probably block it blindly. Okay. Now, this is basically like an infrastructure that's heavily used by threat actors, because to buy a .xyz and a .top, the domain is very cheap, and you can sometimes buy it for free also, and it's actually hosted somewhere which you don't have to worry about. You can abuse these domains pretty badly. And most of the times, if you observe, there'll be a lot of banking domains followed by .xyz. Okay, that's to trick people, saying that it's, it looks like legitimate. Now this is definitely abused. And if you observe this WP includes, this is basically a WordPress site. Okay, now usually how do you find out if this domain is good or bad? Is there's a site called site.check.security.net. It's sitecheck.security.net. Usually, if you find anything that says WP includes, that's actually a WordPress site. Okay. Now, in such cases, what you do here is you just scan the WordPress site and probably figure out and say what actually happens if the WordPress site is compromised or not. Now, usually the site could have been updated now, okay? But usually when you spot these WordPress sites, just scan it. You'll probably find if it's outdated or not, okay? So it'll probably give you a result. I think it's updated back again. I think it's updated, okay? Now, you will know these things. So this site was there in the past that was actually had an outdated WordPress site. Okay. Now, when they had an outdated PHP or a WordPress, the attacker would have compromised the site and you would have inserted a URL that probably redirects to this. Okay. And similarly, this is a genuine site and this actually has been compromised. And if you observe, this is actually a bad IP address. There's something called as virustotal.com. Okay. Now, VirusTotal is basically a combination of 85 to 86 antivirus vendors. Okay. Now, when you give it, they'll probably tell you if the domain is good or not, if it's bad or not, was it abused or not. And if you observe here, in the past, this domain was actually known to have hosted something very suspicious. And then it's all cleaned up now. Now, this is very important. You could probably ask me this question. Why am I giving you these details before we run a malware analysis? Now, these are the key things to be noted because running the malware and understanding the malware is one portion, right? In an organization, the moment when a malware basically runs, you probably have to figure out that the malware is actually talking to a domain or IP. There are three possibilities to it. A malware can talk to a domain just to say that, hey, I have started running. This is called as command and control. Okay. This is called as beaconing or command and control. It's giving a signal and the malware author will have 10,000 of these domains like this in his arsenal. The moment the malware or this bad piece of code runs on your computer, it will establish a communication with one of these domains and say, hey, I've started running. Okay. Now, what do I do next? So the domain will start giving instructions to the malware saying, okay, is it a Windows? Okay, let me give you something. So it will download additional payloads. Now, how does this work? This will bypass all your endpoint antivirus engines because it's all happening through a legitimate process. I'll probably talk about that later. Okay, that answers your first exercise. Now, the second exercise is pretty quick and simple also. A customer usually comes to you and says, this is your second exercise. Just open up your second exercise. The customer usually comes and says that, hey, I have a bunch of information that I found. Looks like we need to do some investigation. Can you do an investigation? You need not run the malware, but I have the malware data with me that actually ran. So you should be in a position to read a report and tell you if the malware ran or not. Can someone probably just go through this for 2 minutes and tell me what makes you, what can you understand out of these things? And then we'll probably head into reversing a sample. Okay, I'll just probably give you 2 to 3 minutes. Just go through this. So whatever I've put it as exercise are real everyday use case scenarios that we face at work. At least I face at work. Sometimes we block something, sometimes it's new, sometimes somebody's done the analysis already. And the first goal for a malware analyst or analysis is not to show that you know something. Okay, if the information is already available in the internet, make use of it. Because the more you waste time in spending reversing a sample, the more the damage it basically does. You should be smart enough to pick up the details from the internet and start adding it to your block list in your organization. And also study the patterns so that you don't waste your time in running the sample again. This is the most essential part. And then the third part is where we will reverse the sample and I'll probably show you. Okay. So can someone probably go through this and tell me what interesting stuff that you see here?
Hello.
Yeah, go ahead.
Yeah, I can see some exe files,
Smart. Okay.
some payloads, which has the malware payloads network first two HTTP links, that is the network payloads,
Amazing.
malicious payloads, and some exe files and some executable files. That is, it's documents which are hashed with the SHA-256.
Smart.
And then DNS, that is domain names, malicious domains.
Okay.
Some of the malicious IP addresses,
Okay.
they found that these are the connections which may be a malicious one, and the URLs, the HTTP request,
Hmm.
and these are the other based on the protocol request.
Smart. So I want to ask you one question, ma'am. So
Yeah.
you sorry, you answered this question, right?
Okay.
This picture basically tells you a story.
Yeah.
Okay. This tells you a story. So don't you feel that even without running a sample, you're able to understand what's happening, correct? Now, can you tell me one thing? When we will run the sample and investigate, right?
Okay.
What are the places that you feel the executables are getting dropped? Can you name a couple of locations that you see here?
Couple of location means I couldn't understand the
The
location
file
means.
locations. Where do you feel that it's getting dropped?
File locations. One is in the first. The payloads are in the network.
No.
Sorry.
So the dropped executable that I showed you here, right? Here is one, and you'll probably see another dropped executable, right? Can you
Yeah.
tell me the path where it is?
Path. Okay.
Yeah.
Okay. So it is executable files are stored in admin, users admin,
Okay. You see a
application.
roaming here, right?
Yeah, roaming.
Roaming. Okay. And you see it's
Others are in
getting
a local temporary files. It's in a local system.
smart. Perfect. Okay. Two things. Okay. You figured out that it is getting dropped here into the roaming or temp. Okay.
Yes.
Now, there should be some means and ways of an entry point for this malware. Am I
Definitely.
correct?
Yeah.
There should be some entry point for this malware, which we have probably have to observe.
Yes.
And you also told me that these are the HTTP requests, correct?
Yes.
Now, when I mentioned a point in the previous exercise, I said once the file runs, right, it's going to talk to the domain name to get more samples.
Yes.
And that is what is actually happening here, correct?
Yeah.
And do you see this? There's a world dot club. These are free domains or bad domains. Perfect. So we can block the IPs and the domain names and everything. But the primary concern for us now is how did this malware come in? Okay. Now that is where you'll have something called as this link. Now
Yeah.
these are called as online sandboxes. You need not always reverse the sample by hand.
Okay.
Okay. You need not always run a malware sample by hand because doing it by hand will take a lot of time unless you're not very particular or very well versed with it. Okay. Now, that is one way of probably doing it. The second thing is you can quickly upload a sample to a service called any.run. Okay. They'll help you to, visualize how the sample had actually run. Now, whenever you saw the whole thing, you know this is a malware, it did something, right? But when you went to the sandbox, this actually a ransomware. And do you see a bunch of documents and PDFs here? Do you see this PDFs? You'll see a lot of PDFs here. And did you see a document here? Correct? Now, the mode of entry for this was actually an email. So somebody got an email and they got a Word document. When they probably opened it, it spoke to these bunch of URLs that we saw in the files here. Okay. And then you got encrypted. Now, this is how the attack basically worked. Okay. Now, this will probably talk about the process that was spun, who was responsible for doing it. We'll probably take a look at it later. Now, this is how you probably make sense out of a report that you see free in the internet when someone gives. Any questions? Are you guys able to understand this? We'll probably play with the real samples now. Any questions? probably see the chat if there are any questions.
Excuse me.
Yeah.
So you are saying that from the mail, the malware is coming, right?
Yes.
They are opening the document, and the document is auto executing some
Yes.
malware within the system, and
Yes.
that is try to access the control of the total system.
Yes. That is what we are going to discuss or do hands-on now in the class.
Okay.
Okay. Now we've seen various places when you install an application and you probably get infected, right?
Yes.
Sometimes it can be a free downloader like document to PDF converter, or some junk software, like VPN software you install or a movie player you install. But today the industry works a way where 75% of the malwares actually come in via email and in a Word document. That's what we're probably going to see now. If you probably have no further questions in these first 3 sections, I'm probably going to skip exercise 3 and 4. It's the same. You'll probably put this app.run and you can probably figure out what it actually does like this. It'll tell you the story again, like saying that what actually happened, how it actually ran. So somebody opened a Word document, and then in that Word document, it started talking to a bunch of URLs. And you can probably inspect the URLs to see where it comes from, and then you block the domains. Okay. If you observe here, when the application was run, it actually runs a bunch of exes. Then it checks for the internet netstat.exe. It has a command line. It does a bunch of stuff, and then probably it activates something. So this is like you will probably understand when you probably take a look at the other 2 exercises also. But before that, any questions before we head to our hands-on part? I'll probably explain the basics of malware Word document in this slide. But before that, any questions?
So why
I have a question.
specifically? Okay, continue.
I
Sorry?
have a question.
Yeah, go ahead.
Yeah, it's a malware hunting. Okay, you have said some of the actors, some of the basic features we can say these are the way to hunt the threatening. So for network, basically in the network, so the hash files are used in the once the system enters into the once the malware is entered into the system. So before entering in the network itself, what are the factors are used for identifying the malware attacks?
Good question. So basically, right. So there are 2 ways to. That's exactly comes to my point. Okay, there are 2 sides to a threat. Okay, the slide that you see here, right? That's exactly what I was supposed to talk about. There are like 2 sides to a threat. Okay, one, the threat itself, right? You have a file, you have a bad file, you create a hash of that file. You know the file will run, it'll call to a network. These are all behavioral analytics of a file. Okay, now that is how your antivirus engine basically works. Okay, now that's why if you see the moment you put a pen drive or a thumb in like a hard disk in a computer, the antivirus immediately says that, okay, this is malware, I'm quarantining it. That's based on signature based detection or file based detection. Okay, now the second thing that you asked, right, I am talking about the fact when I showed you the domain names and IPs, today's malware especially, right, the malware that we are facing for the last 3 years are tuned to bypass internet detection systems or prevention systems. Okay, I'll probably bring a classic example in this case for you. An example, okay. Do you guys want me to explain firewall in a very simple terms? If you're probably up for it, I'll do it in 2 minutes.
Yeah, go for it.
Okay, perfect. Now, firewall is like your security guard in a college. I'll take the college scenario. It suits best for everything. Okay. Now, there's a security guard in the college whose job is probably to check everybody's ID card. If you don't have an ID card, you're thrown out of the college. You cannot enter the college. Okay. Now, in this case, the security guard is basically the firewall or an intrusion detection or a prevention system. Okay. Now, what is the security guard's job? His job is to check for ID cards for students who come in. And if they don't wear an ID card, they are sent back home. Now, this is actually called as a rule. The security guard, who is the firewall, is configured with a rule to check for ID cards. Okay. Now, in a day, there will be 200 people who are entering a college. Let's take for an example. sometimes his job is to just check the ID card. Anybody who has an ID card can probably enter, correct? Now, there will be a lot of bypassing happening. You've asked the security guard only check for ID card, and you're not asked him specifically to check if the ID card belongs to that person or if his face resembles, because there'll be so many students coming in. There will be 4 to 5 people who basically bypass this. Okay. Now they'll bypass this, and then when the management comes to know about it, then you'll probably introduce like an RFID card. You have to swipe, the watchman checks you have the ID card, then the door opens and you go. That is unique, correct? Now that is exactly what happens in an intrusion detection or prevention system. Okay. Now you allow every traffic to come inside your network and go outside your network. Okay. And in such cases, you are looking for malware. Anything that is a suspicious file, anything that looks strange or application, your endpoint detection system will block and it will not allow you to enter. Now, what malware authors are basically doing here is, now if I send the malware or the file just like that, I will get caught for sure. Okay. Instead, what they do is they take a Word document. We'll talk about that in the next slide. And they embed the command to download the malware inside a Word document. Okay. Now, let's come to this point. I'll ask the question back to you. Is Word document a trusted application in an organization or not?
Yes, it's a trusted.
It's a trusted, right? Now, when a Word document is opened, nobody suspects the Word document. It basically runs. Okay. Now that is where these threat actors, they put a piece of code, okay, that when it runs will try to talk to the URL and download the actual malware. Now that is what you saw in that previous example where it was sitting in roaming Microsoft Word Windows. Now, once it probably comes in, it sits in the temp folder. Nobody scans for the temp folder, or it sits in the memory, which we'll probably see. Now, the second thing is, right, once the malware starts running, it will look for a lot of network connections like domain and IP. Now, when you do this threat hunting, you will end up blocking the domains and IPs that the malware is actually contacting. Now, even if your endpoint detection system failed to block the malware, and when the malware actually runs, all these IPs and domains that the malware is trying to talk is already blocked by your organization. So the malware has no value in this case. So this is basically interconnected in a way, the aftermath and the before math also. So does it answer your question?
Yes, so that is the entry point is the IP address and DNS. So we have to focus on that to control
Yes.
the network.
And the entry point, the IP and the domain is not only the entry point, it is also the communication point.
Okay.
Now, if you block the domain or the IP, the point is the malware is stealing something, right? A robber comes to your house and he steals something, okay? And he has to find a way to transport it back or get it out. Otherwise, there is no meaning he'll get caught, right? The purpose is defeated. Now, that's the same thing with the domain and IP. Malware authors will have to talk to a domain and IP without fail. So they have to do, because all the instructions cannot be given in the files. It'll be heavy. That will again get blocked at the network level. So that is the reason that these things actually exist. So this domain name and IP are big, interesting scenarios that you need to. Okay. So I have a question, sir. Before opening document, is there any mechanism to identify that malware? That's what probably we're going to do now. So that is what we're going to talk now, and that's what we are actually going to do for the rest of the class. That's our exercise, okay? But before that, a quick run through of what we're going to do. We're going to hunt the threats from two sides. One, what we saw was the first side saying that, hey, there was a sample in the internet. Do you know about it? This is the domain. This is what it talks to. Let's block all the domains and the IPs so that it doesn't communicate. That is one side, which is what we saw so far. Now, the second side is what we're going to do. Okay, why should I always depend on the internet and see what's exactly is happening? Why can't I reverse a sample and see what it does, how it behaves, and so on, is actually our next half, which we are probably going to do. Now, this is your classic example, which is actually called as mal spam. whenever you see a spam document or a PDF or an image that's associated with the email, that is basically mal spam. Now I'll ask you a question, okay? If I am going to send you a Word document saying that, hi guys, I'm going to hack your computer. Once you open this Word document, you will be compromised. Would you open this Word document or not?
No.
No. Okay. Brilliant. Nobody will probably open this. Now let's play a little psychological game. Now, any threat or any attack or any malware works on a human emotion. Okay. It's basically working only on something called as human emotions. Now, I have always a psychological touch to whatever I do when I work, even with malwares. I believe that cyber attackers play a lot with your psychological behaviors or the psychological aspects. Okay. How? Now, human beings are always inclined towards three things. One is fear, one is excitement, and other is probably greediness. That is a human being's nature. Okay. Now, fear is something that what you see here. WHO has asked everybody to get a vaccine, open this, fill this form, and all of these things. Now, somebody, you get an email, definitely, you want to probably claim your losses because of COVID. Somebody will open this document. This is fear. Second is excitement, saying that this is spam that's actually happening in Europe, saying that if your business is running in loss, the government is ready to compensate. Fill the details. This is in Europe. So this is excitement. You'll probably open, right? Next thing is saying that you've been selected to get the trial vaccine. Do you want to do it? This is actually more of an excitement plus fear, plus also anxiety, saying that anxious, I want to probably get it done. In all the three cases, you will open the document. Now that's when the malware basically runs. If I had asked you to open, nobody will open, but I have a cover for me saying that I'm luring you probably to open the document. Now, whenever you do malware analysis, you probably need a bunch of evidences. Okay. Now, what are these evidences? One evidence probably I showed you was what we saw in the internet. That's open source threat hunting intelligence or evidence gathering from the internet. The second thing is you will run the sample and you will find patterns, evidences, domains, and IPs. Once you probably put together all these evidences, then you'll probably understand saying that, okay, the malware opened here. It's talking to these domains. It's behaving this way. Okay. Now, in a nutshell, what exactly is a malware? We've been speaking about saying malware, malware, malware. A malware is nothing but a small piece of code. Okay. It's as simple as a hello world program. Now, usually the malware takes an input from your computer and gives the output back to the attacker. That's a program, right? You give an input and it gives you an output. So in this case, it's like what is this bunch of malwares? Ransomware, spyware, adware, worms, trojans, and botnets. Now, observe, we just take two examples. Ransomware, it takes input in your computer, which is files. And what is the output? It encrypts all the data on the computer and gives it back to the attacker. Okay. Now, similarly, what's a spyware? It steals your data, gives it back to the attacker. Now, how does a malware usually enter? Now, somebody has to open the door for the malware to enter. A malware cannot penetrate your computer by default. Now, somebody has to open the door for you to enter. Who's actually opening the door? Users, human beings, which is us. We open the door for the malware to come in. Now, how do we do it? That is because of the Word document. Now, I asked you this question, right? Somebody comes and asks you saying that, hi, can you give me a credit card information? Nobody will give you credit card information, right? And if I just send a malware in plain, like a Trojan horse.exe or a file, my antivirus will probably block it. Now, that is where we exploit a space in Word document called as macros. Okay. Every Word document has a feature called as macro. Now, what exactly is a macro? Take a look at this box. The moment I open this box, a cat has to come out and say good morning. I know this doesn't make sense, but still, okay. Now, when you probably open the box, a cat has to come out and say good morning. Okay. In this case, each time when I have to open the box, the cat has to come out and say good morning. It's a repetitive task. What if we can automate it, right? Write a small piece of code and say, whenever someone opens the box, on opening the box, The cat has to come out, say good morning, and has to go back inside and close the box. Now that exactly is actually called as a macro. Okay. Now a macro in a Word or an Excel is basically a small program module. Okay. That, for example, when you open the Word document, it will say good morning. It can display a formula. It can display a bunch of other things. But this got abused massively by cyber attackers. Okay. Now, how did it probably get abused? Now, I told you, right, the moment you probably open the Word document, it'll say good morning and do a bunch of other interesting things. Now, what attackers started doing was, if I send the file just like this, my endpoint detection system is probably blocking it, antivirus. Why can't I put a small URL here? Okay. Why don't I put a small URL here? Right? When somebody opens the document, on opening a document, that will be the bad URL which downloads the actual malware. Right? Now, here comes the question again. The Word document is a trusted process. Your antivirus will not monitor it. Now, anything that happens inside the Word document is again trusted. Now, even though the Word downloads another file, you will not be suspected. Now, that's how these actors work. Now, when the moment you open the Word document, the malware basically starts running. Correct? That is because of macros. That is why Microsoft started implementing something called as macro warning. Okay. Now, if you observe when you open a Word document, it will usually say enable content. I will show you a Word document that we have. We'll do this probably later. Okay. Anyways, we're probably going to do this. Just going to open this. It's a little slow. I don't know why. Okay. I'm going to extract this Word document. This machine is not with you. I just told you, right? There's a reason behind me not giving you this machine. It's a very heavy machine. So, okay, I'm just going to put this here. Any malware that you see in the internet, if you want to try it out, it's actually called as infected, the password. INFECTED. It's a common password that most of the people use. Okay, perfect. So what I'm going to do here is, let's take this. Let's close it. You will see the Word document here. And when you observe that when I open the Word document, usually for sometimes if it's in a docx format, change it to doc so that it runs with all versions of Word. Okay. Docx to docs you have to change. Now, if I open here, the Word document, do you see there's an enable content here? Okay. I've not activated Office, but if I run it, the malware will run. That is why the malware always has, that's why Microsoft has something called as enable content. So why? Because it says on opening the doc, as I mentioned here, when you open the doc, the macro will run. Now, how do we analyze these things? Now, let's go to a Remnux machine and let's analyze a malware. Okay, you'll have a machine like this, right? Remnux machine, leave this machine for now. You guys will have a machine like this. Okay. Now let's start analyzing a real malware. Once you probably see, you'll have okay, go to CD. I'll just show you guys. Once you do an LS, you'll see these three things. Okay. I want a yes, guys, because I don't know if you guys are doing it with me, but probably someone who gives me an S here will probably help me saying that we are on the same page. Okay. Now, do you see something called a CD downloads? And then once you go inside downloads, there's something called as samples. Okay. And you go inside samples, there's something called as malware. Okay. Sorry, CD malware. Oops. And inside that, you'll find one sample. Are you guys here with me so far? Did you guys get in here?
Yes, sir.
Awesome. Now we're going to analyze this malware now. Now this is a Word document. There are like several ways to solve a malware. Okay. We cannot do all of these things in 2 hours, 2.5 hours. Okay. Or 3 hours. So what I thought was I'll probably get you started with analyzing a malware and then probably show you some tricks that I do usually for malware analysis. And then we can have it that way. Now, sorry. The first thing that you guys are probably sorry, gonna do is actually gonna run a sample. So there are like two ways, okay? What we are probably doing here is actually called a static analysis. Okay. Now static analysis is nothing but, there are two things, static and dynamic analysis. Now dynamic analysis is done in Windows where you run the malware. I open the document, right? You open the document, you run the malware, and then you study the behavior of the malware. It's an expensive process because you have a lot of things to monitor when you probably do it. Okay, you have a lot of things that you need to keep monitoring so that it doesn't, you know, you don't miss an eye here. But I will show you that. But let's start with something simple, which is actually called a static analysis. Now, what's the difference between static and dynamic analysis is, dynamic analysis is nothing but you go to the shop, try every clothes, and then you probably buy. Static analysis is nothing but just looking at it and buying it online. Okay, like buying it from Flipkart or Amazon. That's what we're probably gonna do. Now we have a sample here. Okay, this sample is password protected because nobody accidentally should not click on it. Now let's unzip this sample first. I'm gonna do a clear screen. I have a habit of doing it. Type 7z space x. Okay, and whatever the file name that you see here, 7z space x. This is basically telling to extract the file using this compressing utility. Okay, you press enter, it'll ask for a password. Okay, the password is infected, INFECTED. Infected, all in lowercase, is the password. Okay, infected is the password. Once you type the password, and then you will probably see the file which has been downloaded. Now this is basically called as the hash. Okay, now when you, all your antivirus engines basically work on this concept. The moment it sees a file, every file has a unique value, hash value calculated. Now the moment you probably, I don't want to do it, but the moment I downloaded it, put it in my desktop, my endpoint detection system that you see here, Cisco AMP, will automatically block it because it has the hash value of it. Okay, now that is one way of detecting it. We'll also look at something called as behavioral detection. Okay, by analyzing a file, you will know what the file will try to do when it runs. So antivirus engine also has a small placeholders in some places where it will monitor. For example, okay, a Word document or a PDF document is not supposed to talk to the internet. Okay, it's not supposed to talk to the internet. There are only remote cases where if you have a receipt or if you have a payment bill, you can probably click on a link and do it. But continuously, when a Word document keeps talking to a domain or an IP, it's an anomaly. So your endpoint detection system will immediately block it. You'll probably see a pop-up on top saying that, hey, looks like this is suspicious, and it'll block. This is basically behavioral analysis or behavioral analytics or anomaly detection. They'll have small placeholders like small CCTV camera kind of a thing, like a monitoring mode inside the operating system to see if a Word document is trying to access my C drive, is it trying to scan my files? If it sees any of this activity, your antivirus immediately will block or quarantine this file. Now we are probably going to do something related to behavior analytics. The first thing probably that you would do is something called as strings. Okay, now strings, as I told you, is a basic static analysis technique that probably allows a user to take a look at a file even without running the file. Because in Windows, usually in Windows or any other operating system, a file is probably made of a lot of strings that will give you a giveaway to the operating system saying that these are the bunch of things that are actually going to be done when it is run. That's the design of an operating system when it runs. Okay. Now, by running strings is a utility that's present in Linux by default. In Windows also, you can install it. You can probably find a bunch of interesting things, but don't run it. I'll burst the bubble for you. I'm going to run strings from Windows for you and show you first, and then you can run it in the other machine. Okay, now let's see what we have here. I'm going to go to desktop, CDIR. It's always an issue for me with Okay. Sweet. Awesome. Okay. Now here, if you see, I have a bunch of EXEs here. Okay. Now if I run strings usually on an EXE, let's take lab, not the DLL. Let's take one for I agree, and I'm gonna run it. I'll just minimize it. Okay, you guys can see me still, right? Okay. Now here in this case, what I'm gonna do is I ran the strings against this file. Okay. Now if I run strings against a file, it will probably tell me what are the bunch of activities the file will try to do. It is actually copying. The file will copy a file. The file will create, this file will create a new file. It will look for a bunch of activities, and then it will actually access a particular location. It's going to download something like this, or it will do something. Okay. Now a string will give you a very interesting and meaningful fact. Now let's consider this other example. Sometimes strings can also give you domain names or IPs. Now I can probably look up this domain name in the internet and try to block it. So I know that when the file runs, it is probably going to make a contact to this domain name and download something. Okay. It's actually opening something, doing a bunch of stuff. So this is basically called as string. The moment you probably see a domain name or an IP address here, so you see a domain name here, you'll always find something called as internet open. Now, what are these things? These are basically called as Win32 APIs. Now, what is an API? I'll probably put a very simple explanation to a concept called API. Okay. Let's take, for example, we are all going to a cooking class. Okay. All of us are going to a cooking class. Now the cooking class is like a badge. 40 people can probably come and join the cooking class. And when 40 people come and join this cooking class, there's something super interesting about it. Everybody probably in this cooking class will have to do some dish, a common dish. Okay. Let's take, for example, we are going to make pasta. Okay. Pasta is the dish we are probably going to make. Now, pasta has 17 ingredients that has to be made, to be taken, and you have to probably make it. Okay. Okay. Now, the question, you are going to make pasta. I'll ask you a question. Will you carry 17 to 20 ingredients in the pocket or in a bag and go to the class? Yes or no?
No.
No. Why?
If 40 people are there, then we can share the things.
Exactly. Okay, you can share the things. That's a smart thing. So you're going to share. Okay, that's a very good word that I actually heard. Share. As somebody also chatted. No, we can share now. Smart. You can share. Correct. If you are going to share, there should be one thing. The ingredient is common for everybody. Correct. The ingredient is to be common for everybody because all of you are having the same pasta. Correct. Now that is where something called as pantry comes into picture. Now you go to the class, you'll have a big pantry and you'll have probably a small piece of paper where you'll write your recipe and your ingredient with yourself. Correct. You have 17 recipes. You will say, okay, this looks probably needs garlic and it needs some, some seasoning. It needs wheat pasta. I have to boil it. So you have a bunch of instructions and whatever you're probably carrying written in a piece of paper. Okay. Now you go to the class, you go to the pantry, you share it or you take it, the resource, and then you probably put it back. Now that exactly is what a API or a Win32 API is all about. Every program that runs in this computer, right? This EXE that you see or anything that runs, right? If I put all the basic operations of talking to the internet, getting the address, getting the memory, opening a file, closing a file, all of these information, if I probably put into a file becomes very, very heavy. Okay. Now that is why every program that's written on Windows will make use of this Windows Win32 API. Okay. This is the paper that I'm actually talking about. Now it's saying, if you observe, if you read this itself, it's a story. Now it's saying, I hi, this is my paper. Okay. I will be talking to the internet. I'll need an internet connection. So can you give me the API that allows me to open the internet URL and do it? I will probably create a service in the taskbar. I will need some memory. Can I allocate a memory? Give me this method, give me this method, give me this method. All of these methods and DLLs that you see are not packed with the file. Instead, during runtime, it is basically referenced, used, and then destroyed later. That is the purpose of a Win32 API, and that's how when you run strings against a program, you can see what are the Win32 APIs are getting called. And with this, you can probably tell a story. Now, I know in this file, when the file is open, it's going to create a service, talk to a URL, allocate an address, it's going to load a library, and it's going to make use of these DLLs. Okay, this is the power of static analysis. It's also looking for Internet Explorer 8. It's also looking for date and time of a file. It's doing a bunch of things. It's opening something, closing something, and a bunch of other interesting things. So strings is always essential in a static analysis when you probably run it. Okay, I think this Win32 concept is a very complex concept. I tried to explain it very simple to you guys. Hope you guys got it. Any questions so far? Is it boring? Did you guys repent for signing up for this, or are you guys enjoying it?
So interesting.
Awesome. Any other comments? Do you want me to change my style of teaching or change my pace? Okay. Do you want me to quit? Or is it fine? Okay.
So can you explain Win32 API once more? I
Sure.
didn't really get it.
Okay. So what exactly Win32 API is all about is nothing but, see, whenever a program runs in a computer, right? Every program needs an address and a space. Okay. Everything in a computer when it runs, a program when it runs in a computer will make use of the system's memory. It will need a space to store, load, do a bunch of things. Now, if I pack all the programming modules, right, saying that I need to open. So when my program runs, I need this code that actually connects to a socket. I need this code that needs to create a service. I need this big piece of code that needs to allocate memory. If I
Sorry for
dump all of these things inside a file, the file becomes very huge. Instead, I use Windows Win32 API. It's like a abstract class kind of a thing. I define saying that I am going to use Internet API, and you write it in a list and come. The moment the file runs, Windows will look for the Win32 API calls. It says, okay, it wants to open a internet file. It wants to talk to the internet. It needs to talk to a domain. So I see the internet open a Win32 API is being referenced here. Let me give it for you. So Windows will give you the call for this API. And to create a service, if this is present, Windows will tell, okay, this file wants to create a service. Since you have written it saying create a service in this list that you have, let me give you the create service API. That API will have a code, okay, which is inside the crux of the operating system and so on. Now, when you run strings, you can see these Win32 APIs, and you can probably figure out what the file exactly is trying to do. Any questions? Is it fine?
Yeah, I have a question.
Sure.
How the malwares are use this Win32?
Okay, good question. See, any application or a malware application is also an application. Okay. Now, the goal of the malware is probably has to steal something from your computer. Once it probably steals something from your computer, it has to probably give it back to someone. Every program is a normal program. If you see a good program and a bad program, they'll have all these things as common. But the only thing that you will observe in a malware is the malware will probably, I'll explain that when I do the analysis, okay? The malware will always try to write inside another process, a running process, okay? Now that is where you can find out using this Win32 API if the malware is good or bad. Okay, there is no difference between a good program or a bad program. I've never observed something like that. But the only thing that a malware will do it is it will try to inject something inside another process. Once it tries to inject inside the other process, that is when you can differentiate if it's a good process or a bad process. And you can probably see it here when there's something called as get proc address, get list of running process, get this particular process's address. That is when you'll probably figure out, okay, the malware is doing something bad. Okay, so all the malwares are the same in some way or the other, but whatever I've observed is there's no difference between a good or a bad program. Malware is also a program, but it abuses the system privileges in various ways. That's all. Okay, now what a file is not intended to do is what malware basically does. Answers your question?
So, in a practical session, please explain how to find that it is a malware.
That's what we're going to do now. That's what we're going to do now.
Okay.
That is the next step. Okay. I'll see if we have any other question. Then we'll quickly jump into running the malware itself. Okay. Awesome. Somebody had posted a question. Macro may be good. Yeah, macro is always good. Okay. Macro will help you to put formula. Macros can also display pie chart, bar chart. It is good. Now, what malware is basically abusing a good practice is basically what malware does. Correct. So see, we have how do I say? Watching movies is good, but piracy is bad. It's abusing it, right? And you have a rupee note. Somebody prints fake rupee notes also. So the machine that is used to print notes is for a good purpose. The same machine is also used to print fake notes. It's for a bad purpose. So macros also like that. It is used for a lot of good things, but attackers are abusing it. Very simple. Abusing a system is what we probably call about it. Okay, sweet. So whatever you saw here is basic stuff. Okay, whatever you guys saw here is basic stuff. This will not be there in your malwares. Now go to your Remnux machine here. Okay, we are done with this side. Let's come here. Do you see this sample here? Okay, now you see this 9D sample, right? Run strings against this 90 sample. Run this command strings. I'll just run it for you again if you want. Strings 9D sample. Run the strings command against it. Okay. Can you see what is the output? Any interesting that you see here? Like how we saw there, no? Win32 APIs. Can you spot any Win32 APIs here? I'll give you 2 minutes. Just go through it and tell me some interesting patterns that you see here. So iframes are yes, iframes are similar to macros. Iframes, except for the fact, are present in websites, which is hidden. Iframes is actually hidden, and when you open a website, if you probably put your mouse cursor on that, it'll probably redirect to another site. So yeah, iframes are technically similar to macros, but you can avoid by opening a macro, but you cannot avoid opening an iframe. So that's one issue. Oh, you want to probably see the command again. Somebody wanted to see the command. Strings space. If you type 9 and press 9 and tab, okay, I'll show it to you again. Strings 9 and you space D and then put tab, it will complete it for you. Press the tab key to complete it for you. And then press enter. So quickly, we have time till 12:45 or 12:50, then we break for half an hour and then come back again. So we have quite a bunch to cover. So I wanted the basics to be very strong. That's why I take a lot of time to get you to the basics. See, about malware analysis is always about why you're doing something, which nobody teaches you that usually. We just take a sample, we just reverse it. Any books will probably teach you that, but you have to understand why you're doing it. So that's why I just take a lot of pain in doing it usually. So yeah, tell me what are the patterns that you've observed here so far? Any patterns that you guys observed here?
So are all the strings part of this Win32 commands?
No. There are a lot of strings here. You have to tell me that if you see any Win32 commands. So your goal is to go through this and tell me, do you spot any Win32 commands? If yes, what is it? And what are the other strings that look appealing to you? If you see something gibberish, it's fine. Tell me that you're seeing something gibberish. I don't understand what is it. But tell me the nature of the document. What is it doing? Do you see any Win32 command? Uh, do you see something strange?
Auto open command is a
Awesome. That's a good catch. Okay. You saw an auto open, right?
yes.
Now, what could that be?
That is automatically open a document,
Perfect.
malware file.
Hold on. So auto open is nothing but when you open the document, what can get executed?
It is some malware links or whatever the
No malware. What is the term for that?
opening a file or link.
No. We discussed about it some time back. There's a right term. You have to use the right terminology here. We just spoke about it. Somebody asked me a question also some time back.
A macro?
Exactly. It's a macro.
Okay.
Correct? So when we saw the slide here, right? Do you guys see here, right? Automatically when it opens, the moment it actually opens, something gets executed here. Am I correct? So that is basically called as auto open. The moment this opens, the document opens, there is going to be some small piece of code, which is the macro, will get executed. That can be the URL that it downloads. That can be anything. Very smart spotting. Good. What else do you see? Can someone tell me the Win32 API is here? What else can you see here? Any interesting ideas? Do you see any Win32 APIs? Do you see any meaningful strings?
Some IDs are there within the codes.
Yes, there are some IDs are there. Correct. And you'll see some patterns also here like this. You'll see something called a Shelby and a bunch of patterns. Okay. Do you want me to give away the answer?
Name 32 some.
Yes. Those are all usual calls that actually happens with Windows.
Okay.
You see document auto open. Okay. Now I'll tell you the trick here. Okay. Now Win32 APIs can be spotted only for an exe. Okay. Win32 APIs usually are spotted when you run an exe. In a Word document, when you run strings, you'll probably be able to see the code or the macro code that is actually hidden inside the document. In this slide, if I run strings against this Word document, I can see this entire stuff. Sub, simple, macro, good morning. I can actually see it here when I run strings. But unfortunately, this is a complex malware. Okay. Now, when I ran strings, I could understand two things. This is a Word document. When I open this Word document, there is some macro setting which is going to do some nasty stuff. I need to investigate that nasty stuff and probably see what exactly it is. Okay. See, there are two things. Okay. The attackers usually have these type of string names starting with LQ or WQ. Now, if you probably Google it up later with these patterns or these patterns, you can probably find the family of the malware. Usually threat actors, they have weird string names as starting, which probably indicates the owner of the threat. Okay, they can be a group from Finland, they can be a group with a different name. There are groups like Lazaria Spit, APT33, Brothers of Kazov, there are like Venom Rats, there are a lot of group names. So they will have a small string embedded inside it to show that they are the people. Okay. Now here, whatever you see in the screen is basically called as obfuscation. Okay. Now, if I probably, let's take an example here, right? If I probably had put it saying that simple macro good morning, I can easily find out If there is a domain name or an IP address, I can just copy paste the domain IP address from the strings and block it. Like how we saw it here, right? We're able to see the domain name, IP address here. I can easily copy this domain name and block it. So attackers usually want you to be confused. Okay, now that's why they've obfuscated the string. Okay, obfuscation is an art of concealing the document with junk characters. Only when you decode it, you can find the real characters. Okay, so this document is basically obfuscated. Now that is when you will have to use some tools that are actually there in this Remnux machine. The machine that you probably see here is actually called as Remnux. Okay, now the Remnux machine is mainly built for forensics. You can probably download it in the internet. I have put some samples and given it to you. You can constantly download stuff in the internet, and then you can probably play around with it. But before that, the very, very important thing. I think all of you would have watched my video. Make sure the network setting is only host only, and it is not talking to NAT. If it talks to NAT, the malware, when it starts running, will attract your internet connection and it will start executing, which will create a big problem for you later. Okay, if you have watched my video and set up this, make sure that your network is on host only mode and not in NAT mode. Okay, now, so there are so many tools available in the market to sort this problem out. And one such tool that we'll use two tools here to understand what the sample does and how we'll probably decode it, is using something called as OLE tools. Okay. Now, OLE is actually nothing but object linking concept. Okay. Object linking is probably a concept where every Word document is actually like an XML tree. Okay. It's an XML structure. You have the header, you have the document, and then you have the bunch of macros embedded inside it. Now we use this OLE tool to probably look into the file and see what exactly the file comprises of. Now by running the OLE, you can probably even look inside the file for the macro code even without executing the file inside of Windows. Now that's what we're probably going to do in this static analysis part. Now, before that, okay, now I'll probably show you this OLE dump. The tool's name is actually OLE dump.py and space give the file name. Okay. This is the file OLE dump.py, press space and then 9 tab, it'll give you. Now, there are two ways of doing it. Okay. If I don't usually use tools, now how do I do it is, what I would do, this document file is there, right? I will probably convert it into a zip file. Okay. And once I probably open the zip file, I can actually see this tree structure by default. The tool is instead doing that for you. Okay. By default, you can convert a Word document to a zip file. Once you convert it to a zip file, it will show you this XML tree structure. It's a tree structure. It will probably show you. But the tool here, what it is trying to do it for you is to automate the process for you. When you run this tool, it's a Python-based tool. When you run this tool, like this, it will tell you these are the junctions where the macros are living. Okay. Now these are the junctions that the macros are basically living. And you probably need to look into these aspects where these will probably have macro code. Okay. Now, if you observe in a Word document, every the data that you see here is stored inside something called as a stream. Okay. Now, this is actually a stream. A document is where you have a stream and all the data is probably stored in form of a stream. It has sections. Okay. Now, what interests us is something saying that I know this one macro here, two macro here, and three macros are here. I want to know, if you observe here, there's a unique macro name which is encrypted, obfuscated, right? Usually it will say macro good morning, macro good evening, macro download, macro malware. But if I see it easily, I can find it easily. So that's why the attackers have confused you by obfuscating the content. Now, in order to inspect a particular section, you have to probably type OLE dump .py space. Now, what is the stream number? My stream number here is basically 13. 13 looks suspicious for me. And I'm saying, okay, go look inside stream 13 for me. In which file? In this 9D file. Okay. I'm saying, dude, just get in, use ole dump. I know where the macro lives. This M symbolizes macros. Okay, this is where the macro probably lies. And then let's run, look for the particular stream against a file. Now, why am I explaining all these things is when you do malware analysis, never run the tool just like that. You have to understand what the tool basically does. So I've taken a lot of pain in the last so many years why I do this analysis. I understand the tool usually. There are two reasons for it. When you understand the tool, there will be some limitations for a tool so you can develop a tool in the future. Okay, that's a good practice to analyze malware. Awesome. When I press enter, it gives me a hex editor view, which again does not lead you anywhere. Correct? I am not able to understand anything out of it. It gives me a hex editor view. Similarly, if you run it against the other strings also, it does not, other streams also, it does not give you no value or output. Now, what do we do in such cases? There is one more tool actually in such cases, which is actually called as olevba.py. Okay. Now, what this basically does is just give the olevba.py does something very, very interesting. Now, it's an automated tool that will look for keywords like open, auto open, and also look for strange encoded or encrypted content inside a file. Instead of us manually going, dumping the stream and doing everything, it does it for you. This saves time. Okay. I can still pull out each string, go through the hex editor, look for content and do it, but it's a big, big time waste. As I mentioned, the faster you solve the malware, it is good for you to block the malware so that it does not create a damage. Now just run this olevba.py against the tool and press enter. Okay. Now you will probably see it that this is looks like some code, which means the moment you open the Word document, which is actually sub is the function, okay, in VBA code, the moment you probably open the document, this big bunch of code is getting run. Okay. And you don't see anything familiar like a HTTP or a HTTPS or a URL or a domain name or an IP, nothing. The whole document is obfuscated. Usually 4 to 5 years back, we used to have domain names, IPs, and a bunch of code that was basically running. But it was easy, right? The moment I run the tool, it will give you everything. I can just copy paste it and block it. To confuse the attacker, the file is being run. Now, this is actually a COVID specific malware. All the malwares that we're probably dealing today are COVID malwares that came a couple of months back or 1 month back or 3 weeks back, I guess. Okay. Now, it says that it may run an executable file, which is what we are suspecting. It's downloading something, it's going to run, and it is actually hex encoded. So there's like hex encoded, and there's sometimes base 64 encoded is detected. Everything is obfuscated. Now, you know the logic. When the actual programmer runs, when you open the document, the attacker has some logic which will probably convert it into a normal code, and then it will call out to a real domain. Now, our task is to find out what exactly this Word document will do when we open it. Okay, we're probably gonna not exactly reverse, but we're probably reversing a doc malware here. Okay, we're seeing what exactly happens here. So for your convenience, if you go to accessories here, you see this arrow kind of thing, right? Go to accessories, go to file terminal manager. If you go to downloads, samples, malware, I've put it in a Word document for you so that it saves you a lot of time. Okay. I want you to go through this code for 2 to 5 minutes. We are going to not decode the entire code, but we are going to find out the logic, what exactly this attacker is trying to do in this case. And we will have to find the logic, what it actually is happening. Okay. So I want you to go through the code. I also don't know what is VB code, how it works, but I know a little bit of tricks and tips and tricks of the trade. So which I learned on my own when I Googled it. I'll teach you that. So you need not know any programming language specifically to solve a malware language. I mean, malware. You probably can Google up, quickly read about it, and then you solve it on the fly. Many of these researchers do that way. So just let me know. Just go through this, code and tell me what exactly it is trying to do. Okay. And then we'll probably decode a very little portion of it and then we'll leave it. Then we'll go to the next sample because this is the way to decode it. And I'll show you how the same sample can be decoded when you run the file. That'll show you. But for now, this is a tedious process. I want you to go through it and tell me. I'll give you 2 to 5 minutes. Just go through it and tell me what do you guys observe here.
Shyam sir, may I ask you some questions?
Sure.
Yeah. See, I'm pretty new to this cybersecurity or this thing. I'm trying to learn the concept here
Okay.
based on what I learned from this workshop as such. I'm trying to re-enter the field. Okay.
Okay.
So till now, what I understood that we have malwares and we have various ways by which we can detect it as a malware, right?
Okay. Yep.
Yeah. So now with these tools that you have mentioned, that is the OLE dump and OLE VBA, we can get more details about or whether it has a malware or not. Am I right?
Yes. Whether it has a malware or not, and what sort of malware. What is the file trying to do? We are trying to find the behavior of the file.
Okay.
Okay.
Now,
When you
how is
find,
it?
go ahead.
Yeah, sorry. How is it going to help us? After knowing the behavior, what are we trying to achieve? What is the aim for the whole exercise?
Okay. The aim for the whole exercise is we are probably going to find out the domain name and the IP it is probably going to talk to. Correct? And I told you,
Okay.
right? The moment you open the Word document, it's actually going to talk to a domain name. Am I correct? Now, if I block the domain name or the IP, even if the malware sample runs in the future, it cannot communicate to the command and control, which is the IP or the domain name. Our
Okay.
goal is to find out what the malware exactly is trying to do and who it is trying to talk to. So we're trying to decode it. And we're also looking at one more thing saying what are the various ways attackers are coding the malware to evade detections. That's what we are probably going to see.
Okay. Okay. The last one, yeah, kind of makes sense. So if I write a machine learning or machine learning algorithm, am I going to try for these various ways in which they are trying to encrypt, or am I going to?
So that the point was my last point that I actually wanted to end the talk with. Now, since we know that you will all use machine learning to look for commands like auto open, shell, run, download, okay? Now, these are the
Okay.
keywords that will probably be spotted initially. If I give the sample now, if I give you a plain sample, and if you run it against your machine learning engine, right, you look for these keywords. Am I correct?
Yes. Okay.
Now that is an easy process so that you can do a behavioral analysis and say, okay, in X sample, these were the same patterns that were observed. So let's block it as some family of malware. Now to defeat machine learning to defeat the machine learning as well, all these contents are basically obfuscated now. Okay. You can't even
Yes.
spot one normal command here. Am I correct?
Yeah, I found some command here.
Okay.
In the LYGN function, there is a URL link is there. It's
Smart.
represented to colon, two slash, forward
Yes,
slash, colon, and at the rate. That is some website
you are correct.
domain name that
Yes,
we represent, or at
you
some
are correct. Yeah. I'll come back to you, ma'am, on that. But Sita, ma'am, you asked me one question, right?
Sure.
So this to defeat you, basically from not doing machine learning. Now, this is a lot of time. See, in malware analysis, time and money are very important things. Now, isn't it an annoying task to find out what exactly it does and then extract the attributes from here and then pass it to your engine? It actually takes an extra half an hour time. So
Correct.
this
Okay.
can also be this also serves as an attribute. The keywords, the call functions, and this macro can also serve as an attribute for you to machine learning. So still tomorrow when something comes, but you cannot concretely tell what family it is, but you can tell definitely the document is malicious. Now, that is how antivirus engines also work. They have the engine that detects these things. Even before behavioral analysis, they do a static analysis on the file, they have pattern matching, and they do it. So if you take the machine learning aspect, in the end, once you finish everything, once you execute everything, you can probably feed it and run probably a random forest to say if it's file malicious or not, or also use a bipartite graph saying that these were the pattern sample XYZ, and these were the domain names that we extracted from the samples, and they are interconnected to each other. So using a bipartite graph, you can probably tell in the end saying that these attributes are interconnected, or you can also probably use a bag of words, a bag of features to say what overlaps or intersects between two samples. So that's the goal.
Okay.
Our goal is to get the pattern, mine the pattern, and find the IP address of it.
Okay. Yeah, got it now.
Answers, right? Makes sense, no?
Yes. Thanks a lot. Now
No problem.
it's much better.
Awesome. Cool.
Thank you.
No problem. Okay, ma'am. Okay, fine. So we found some patterns. Okay, some people basically, I think Santa Devi ma'am probably told me that she saw a URL somewhere. Correct? www dot here. Am I correct? HTTP. You'll probably see a URL here. Okay. Now, what you can probably do it here also, you'll see probably a HTTP. There you'll see a URL here. Okay. Now, what exactly happens in this case is when you always reverse a document like this, which is basically you have no clue, never bother about these things. In Visual Basic, I also Googled about it and learned. Okay. So when I see this, right, in Visual Basic, in VPA, usually in this, when you see these things, no, these are all dummy code. Even if you don't declare those variables, or if these variables are not probably called, they'll never throw an error. It will just check for these things, it'll print or it'll assign itself to this, and then it'll end the loop and move on to next. These are basically non-meaningful or unmeaningful code that you basically observe in this case. These don't do anything, to be honest. So don't ever bother to look into these things. They just assign a variable, end a loop, assign a variable, end a loop, and so on. Okay. Now, when you always go through such code, when you reverse, always look for the terms that you're familiar with. Okay. Now, there's some bit of common sense is also involved here. Okay. Now, what is that common sense? I also psychologically think from this standpoint. See, the attacker is basically jumbled it, mumbled, jumbled, or obfuscated it, right? He is a programmer, so he has to also decode it, right? So there'll be some point where he has to strip these characters, split the characters, join a character somewhere in the code. So always look for the terms split and join in some part of this code. There will be somewhere where split and join will be present. Now this is a little complex sample. Okay. Now if you observe split, it's actually string reversed here. If you observe split, it's string reversed here. So you will find something called a split, S-P-L-I-T. Okay. So this guy is splitting some strings and joining some strings. And then if he does a string reverse, he'll be able to get HTTP www.diman dot some domain name is here. Now that will probably give you an answer. Now once you have found the pattern, now you know the pattern, and you always feel these caret cases if are junk for sure. These are all caret symbols are junk. When you remove these caret symbols, if you observe there's a word set. If you observe there's a word set here. If you come down here, there's a word called set. So they are trying to set some variable, and if you remove all the caret symbols, this is actually what the keyword called command, CMD. So they are trying to set a variable, they are trying to do something, and if I remove all these caret symbols, this will probably lead you to www. Okay. Now this is the first way of cleaning up the code. This is a very, 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 very lengthy process. Okay. I'm just showing you the methodologies, how to do it. I usually take a paper, I take a printout of it, I sit with my pencil. I love doing this. Okay. But it's actually a total waste of time if you do it. But you will learn a lot of patterns. You see a for loop here next. If you remove the caret symbol, you will start getting the hang of it. There's a for loop here. It's going to run a loop. It's going to do something interesting here. And if you keep removing the caret symbols, you'll probably understand. But you need to know one more logic. Somewhere, these type of keywords can never be obfuscated. Okay, these type of keywords can never be obfuscated. Now there's something called as key string. Okay, key string is what I see here, right? This is actually called as key string. Now if I Google about key string, so key string is nothing but something very interesting. I Googled about it, I didn't know about it. Okay, now the key string, basically what it does is it actually converts like a number to a key. Sometimes a key string number 33, 43 can be a shift control, can be a shortcut key also. Okay, there's something called as key string. I have given it in the notes for you. There is one URL, okay, which has got a very good collection of key strings. Okay, when I just inspected this key string, you will know that there are a key string combinations for this, right? Number 36 is a hash. So usually what attackers do in several samples is there'll be a lot of, this is a busted pattern. Usually what happens will be a lot of numbers. There won't be HTTP like this. There'll be a lot of numbers. If you assemble the numbers, you'll get HTTP www dot some numbers there. Okay. That's one way of doing it. The second way of probably doing it is, here if you observe, I told this, right? All of this is dummy. If you add this, you won't even get an error. It's all of these things are dummy. But I observe numbers saying this. So this you have to add it. It will throw an error if it's something wrong. I think this is 67 if you add up. Okay. And if you come this side and add up, this is basically what, I'm very bad with mathematics. 77. I think it's 63 and sorry, it's 67 and is it 77? It's 67 and 77. Command line, which is nothing but, if I run the URL in the browser, it's probably gonna be monitored. Instead, what it is trying to do here is, I'm just gonna go to the Windows machine and show you something. Instead, it's actually running a command line. It's saying from the command line, do a run and call to a URL HTTP something www.com, download a file and put it inside a temp folder. If you probably run through the whole thing manually, you will get this answer. Okay. Now this is one tedious way of reversing a file, but there's a simpler way of reversing the file. I'll probably show you that simpler way of reversing the file, and then you can probably go for a quick break. Okay. I'll show you two methodologies to reverse this file. Okay, two interesting methods you here. Any questions so far before I go to the next section? Can you repeat the string 9? Okay, I actually answered the question. Okay. Any questions so far? Are we good? Can I go to the next model? I know it's sometimes way above your head, but this is how you probably reverse malware. So this is like the most simplest way to teach you. It's just making you do baby steps so that you don't hate this subject. So, okay, can we break, sir? Vinod, sir, can I have? Okay, probably we'll come back from the break and then we'll do it. So when we come back from the break, we'll do two things. One, I'll show you how do you do it in my Windows, and quickly we'll probably jump to the memory forensics. Now, what if you don't have any sample like this in your hand, only a memory capture of a computer? How do you go through that, and what you exactly do is what I'll probably show you. Okay. Awesome. Okay, we'll break. We can probably come back at 1:15 and then we have, yes, sir.
Yeah. Thank you. So can we break for half an hour, Shyam? Is it okay?
Yeah, please.
So I would request participants, like we will break from 12:45 to 1:15, and let us assemble by 1:15. We will be using the same link throughout today. So kindly requesting all of you to please join us by 1:15.
I'm going to mute my stuff,
Yeah.
my video.
Yes.
I'll come back again at 1:15 and then we'll continue from there. Okay. I hope you guys enjoyed the class. So we'll come back again into the interesting stuff. Thank you. So we'll come back again into the other bunch of interesting stuff. Thank you. We did static analysis here. Now we are probably moving to this machine where we'll probably do dynamic analysis. Okay. I'm going to clear off the screen because I have to do some small little bit of tricks of the trade here. Okay. So I will be involved in doing something interesting here. So, okay. So what are we probably gonna do here? Interesting. Now what we're gonna do is we're gonna run the file here and monitor the file. Okay. This is dynamic analysis. What is monitoring? Anything in Windows, if you observe, is basically a process. Okay. So these are the basic things that basically happens in a Windows. I'll probably show you those things. So there's something called as process monitor. Okay. The process monitor that you see here will actually monitor every running process in your operating system, Windows. Now, the logic behind Windows is every process has a process name and a process ID. And then it does an operation. These are the APIs. These are the Windows APIs. This process is trying to read a file, and it is trying to read a file in this path. So when this process is probably running, the process will say, hi, I'm this process name, and this is my ID. And I want to access this location, access this file in this location. My operation is basically read. Okay. Now that's how every process in Windows probably works. Now you need to understand two things. Everything in Windows, if you observe, is memory based. Okay. It's solidly memory based. Now your memory in Windows is like a doubly linked list, and it's a bunch of pointers. Okay. Now every process will have a process name and process ID. This is basically in Windows, especially, this is like a token number. Okay. Now if you probably say token number 2032, when you go to a hospital, somebody probably says, who's 2032? And I'll probably put my hand saying that I have the token. Okay. That is like a token number. Once the token is done, once the patient probably exits, the token will probably go to another patient who comes next or sometime later. Okay, there is a count for it. Now the process ID is the token number and the name associated. So you can identify either with the name or the token number or the name. Okay. The next very important thing is a locker concept. Okay, say my locker is 2032. Okay, and every process in Windows, when you observe, okay, has a locker space, which means each process gets a memory allocation. Okay, so that when the process runs, if it stores variable, if it wants to store code, if it wants to store something, that process has a process ID, has a memory, has a location in the memory where it can load, save, and pump data. Okay. Now this is like a typical locker space. You have a key, you have a locker, you open the locker, you store whatever you want. But the sad fact in Windows remains is, in Windows, you can basically request saying that, can I look into locker space 2032 or 1896? One process can access another process's memory. Okay. A process can access another process memory. That's by default for troubleshooting purpose. Windows was built for that. It's like saying I have a locker number 22. My friend wants to say, can I store in stuff? With my consent, I'm giving it to him saying, okay, you can also store your stuff. Okay, but it does not work in the bank that way, right? But in Windows, for troubleshooting, right, one process has to troubleshoot another process, means it has to go inside the process, look into the ID and the memory and troubleshoot. Now, this was heavily abused, is being abused by malware and malware authors. Now, if you see here, whatever you see on my screen is a legitimate process. Am I correct? Whatever you see is basically legitimate process. Now, if I am spinning a bad process called malware.exe here, my operating system or my antivirus will look for it and kill the process immediately. Now, instead, what malware authors do is, you saw the doc malware, right? The moment you open the Word doc, it's going to download an exe, which when it runs will look for a legitimate process. It will scroll through the list of legitimate process using the process API, Win32 API. Get me the list of process. So it will ask for a list of process. Okay. Now let's take for an example, Windows 7 has a process. It's just an example process. Okay. Windows 7. Let's take a very interesting example. Let's say that Windows 7 has a process named, for example, let's take management. Let's take this just dummy example, right? Management agent host.exe. Okay, this is called as main agent host.exe. Okay, now Windows 7 has a flaw, that this agent host.exe has a small issue that any process can probably talk to it, get inside it, and it can use its memory. Okay. Now, when the malware runs, it first looks for the list of process using the list of process API and then hunts for this particular process. The moment it gets the ID and the name, the malware will inject the piece of code or the malicious file inside this process, so that a legitimate process, when you look from outside, it's a legitimate process, but when you look inside, it's an infected process, so that the malware stays undetected. No antivirus engine will probably comment it out. Now connect the logic here. Word document, legitimate process. Once you open the Word document, it is running a macro, which is downloading a file in a location, again legitimate. That file automatically will run using CMD. We saw that, right? CMD run shell from the command line, which will in turn inject into a running process. This is, in a simple words, is called as a process injection technique. Okay, this is what malwares basically do for a concept called as process injection technique. Now we are going to monitor the list of running process and also do something very, very interesting. We're going to do two things together, two approaches combined together, to see how we can catch hold of this running process and also spot which process is probably getting infected here. Okay. Okay, now here I'm just going to show you. I'm going to filter it. I'm sorry, I'm going to clear it. I'm going to monitor all the processes. Okay, I'm not capturing anything for now. I'm just going to clear it. Okay, now meanwhile, what I'm going to do is something very, very interesting. I'm going to run this. Let's see what happens. I'm also doing something super interesting. Now, our goal is probably to catch what is the domain or the IP that it is probably talking to. Correct? Our goal is probably to catch the domain or the IP it is probably talking to. So for that, we'll use a small trick, okay? Saying that I have this domain, right? If you see, sorry, this machine that you see here, right, is my Windows machine. Okay. Now in this Windows machine, if you know networking basics, what happens is every machine will have an IPv4 and IPv6 address. Okay. Now, one way to probably do the IPv4 and IPv6 addresses, let's see what is the IP address of this computer. So the IP address is 172.16.76.130. Okay. Now what I'm going to do is I'm going to set an IP address here for my Windows computer saying 172.16.76.131. Okay. These two IPs will be in the same subnet. These two will be in the same subnet. Okay. So that these two machines can probably talk to each other. Okay. They'll not talk to the internet because they're host only. They'll talk to each other. Now, if I give the default gateway as 1 here, right, that means it has to talk to the internet. Now, what I'm going to tell you is whatever traffic runs in this Windows machine will go to the Linux machine. Okay. Whatever traffic or whatever I serve from this machine, everything, or be it anything that's happening in the machine, should go through my Linux machine. So what should I do? I should probably give 172.16.76.130. Okay. Now we saw our goal is to extract the domain name and the IP address, right? Now, if I ask who's google.com, if I type google.com or facebook.com or apple.com, your DNS will answer, which is 8.8.8.8. Now, Google will answer usually saying, okay, this is the IP address of this. This is where it is. Now, we are not connected to the internet. I told you, right? If we connect to the internet, we'll get infected. Okay. So we are not connected to the internet. Instead, what I'm going to tell is, let us ask our Linux machine to answer all our DNS queries instead of Google. Now, for example, when the file runs in this computer, okay, it will run in this computer and it will go and ask, okay, I have an IP address I have a domain name saying abc.xyz. What is the IP of it? It will ask. If it's 8.8.8, then Google will probably answer your question. Okay. Here we don't have internet connection, right? Instead, I'm going to give my Remnux or the Linux machine's IP address and fool the malware saying that I will answer all the questions. All you need is someone telling you some IP address. This file machine will probably give it to you. Okay. Now this is a very, very important setting that nobody usually talks about in the internet or in the books part, because people struggle with malware analysis environment usually. Now, this is the trick. We're going to do two things: run the file, decode the file also, and also figure out when the file runs, what are the domain names and IPs it is talking to. So you get a win-win situation. You also got the list of contents inside the file, what it is doing, and you probably also got the list of domains that a file initially is talking to. So you do two things at the same time. Okay, I pressed OK. Okay, I'm gonna do this. Okay, I think I have another machine running. I'll probably kill it. Okay, let me not do 131. I'll probably do 139. I think I have a bunch of machines running in my thing. So okay, so I gave 139 in this case. Awesome. Okay, let's say I think my network has got identified. Okay, so we will run a program called fake DNS. Now, fake DNS is a small Python program that mimics a DNS activity. Okay, usually when you ask saying who is can you tell me the IP of google.com, some IP will come out as a part of a DNS request. This will mimic a DNS request. I'm running this. So usually this is how a DNS query is there. It says query name, what is the A address? Some address it will probably give you. Okay. Now let's see if our machine is responding. So let's say the malware is running. Okay. Now the malware is running and the malware is asking for iambatman.com. Okay. Usually Google answers it. Okay. So usually Google answers this. So it's okay. Allow access. Oh. So usually Google answers it. Here somebody else has answered for us. And if the malware probably makes a connection saying 123.xyz.com, then this guy is answering. So now when the malware runs, usually malwares check for these DNS requests. If they don't get a DNS response, the malwares will not run. They are called as evasive malwares. Now we've defeated the concept also. Now when my malware runs here, I will be able to see what it is running, and I can also get the domain names and IP address and block it right away. Also study the behavior of the malware. Okay, now let's try this out. Now we will capture the process that's actually happening, okay, when it executes, and also get the domain names and IPs. Now this is one way of extracting IP and domain name from a malware sample. Now there's one tedious way of also doing it, which is what I'm going to do right now. Okay, now I'm going to do something very, 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 very interesting. Okay, now what I'm going to do is, instead of doing it the way that I am doing it, there's another way of doing it. Now what I can actually do is, if you are a developer, then probably you find it interesting. You can probably run this inside a developer model. Okay. Now why I'm doing this was, when you run strings against this particular malware, okay, you will not get any strings output. Okay, because the malware is heavily obfuscated. Okay, your OLADE tools will not work. You will not have the strings working. And the only way, the way that we did also will not work. The only way to do is to run the malware and find out what are the domain names and IPs. But there is one option. If you go to developer tools, okay, and you go to Visual Basic Editor, you can see the form elements of this malware. Okay, now if I right click on this and see, it says document open. When you open the document, same thing. This will not be visible in your tools because it's obfuscated. The moment you open the document, it's basically going to call out a domain name. Okay, if you open the document, it's going to call out another, no, sorry, not a domain name, another macro. So this is the macro. So this LQ6N, can we see it? See, we have this LQ6N here, correct? Now let's view the code. So we have the same set of issues. Okay, we have the same set of issues here. Look at the code, it's obfuscated. It's the same confusing. This is the same format that most of the authors are doing. But in our case, I told you the same thing, right? We can look for split and join, and all those things. We can do it. But there's one more way of doing it. Usually, this is like a very cheap trick. Okay, it's a very cheap trick that you do. But there's something very, very, very interesting that you can probably do here. Okay. Now, what's the interesting bit? Now, I have to enable the macro again here. Okay. So what you have to do here is the super interesting trick. Now, instead of going through the way that we did, let's do a super cheap trick. Now, whenever you see here, right, in this, there's a function, there's a call, there's a function. Don't bother about these things. You will see a lot of these variables are getting assigned. Okay. You see a lot of these variables assigned. And if you see here, there's something called as help context.id, which actually says it's actually looking for some sort of an attribute somewhere. Okay, if you see the object, it's actually looking for some attribute here. So something is hidden here somewhere. This is a tedious malware. But in order to solve this tedious malware problem, this is the most cheapest trick you can ever do. Come down, keep scrolling down. Okay. Now, if you observe here, this will be the last variable that's being assigned. Okay. This is the last variable that it's actually being assigned. Now, the whole program. Okay, can someone mute yourself, please? Okay. So when you see the whole program actually running here, this will be the last variable that's actually being called here. Okay. Now the program logic is this will store something and print out something so that the attacker, when he runs this document, there should be some command or some domain or an IP address which is probably pushed out, which will be getting called at some point of time through a run or a command. That's the logic, correct? Even though it's highly obfuscated. Now, this is like the most cheap skit trick what you can probably do. What if we print that thing out? What if we print this out? A simple print, which I think it's called as debug.print. Okay. What if I print this out? Let me print this out. And when I print this out, it will probably give me the answer that I'm actually looking for. Now, why am I doing this? The attacker will also have debugged the program in the same way. Okay, in order to test it out, he will have to print it to see if it's printing it correctly. And that's what he intends to do. So in order to monitor this, we'll probably use an immediate window, a local window, to see actually if it's printing out correctly. Okay, let's print it out and see if it's actually printing it out correctly. Okay, sweet. So what we would probably do in this case, I'll probably maximize this a little bit for you guys. And yeah, so let's do this. So I'm gonna run this and print it out. This is the portion it's where probably gonna print out. So that's being said. Now we observed a lot of strange things here, right? We saw some properties and all those things. Now, sometimes what attackers do is they hide inside VBA forms. Now, this was an accident discovery that I did. When I did this, I opened this Word document and it was a little strange, saying what is happening here. There's nothing here. When I actually kind of maximized, I found out there are a lot of elements that are actually hidden. Okay. Now these are hidden elements. If you move this one by one, you'll probably start unearthing a lot of things. You'll see some values here. Now, usually what happens here in this case is sometimes there'll be something called as HTTP inside this control tip. So whenever this value is called, H value is earthen, then TTP WW, or it's RUN. So these codes will be hidden. See here, you have the word P. So they'll assemble the word saying PROCESS or SHELL. So this is to evade detection by IDS or IPS. Okay, this is one way of solving it. Okay, the other way is probably run. Now let's do this. I'm gonna close this out. Okay, and I'm ready to run this portion of the code, which is basically when you open the document, this is going to be triggered. I put a print statement there, so it should print out the answer. And also, let us actually start monitoring to see if it gives you a output. Okay, we'll do everything at one shot. This is like a combination of methods. I'm going to enable content. Yes, I'm going to enable content. I made changes. So I'm going here. I am quickly opening the Visual Basic editor. I'm going to run this section of code and it should print out something. See, it printed out something, right? This is basically a PowerShell. Okay. Now, this is extremely hidden. That means when this document is opened, it has a PowerShell. Now, PowerShell is a utility in Windows which operates like a command line system. If I probably download, this is basically to download a file. If I go to the browser and download, if you see in the process, if I go download, it'll open up something like saying that chrome.exe. So that's a suspicious process and your antivirus will flag it. Okay. Now, similarly, this is a PowerShell and this is something like encoded. We'll decode it now. Okay. You will decode it with me. Okay. Now, This is a PowerShell. Now I know when the document is running, it has a PowerShell, which is actually calling to something for some domain name or some interesting thing. Now, meanwhile, our fake DNS also got a bunch of XYZ domains. These are bad domains. If you probably look up for these in the internet, they are infectious domains. Now we got the domains the malware is talking to by using this technique, and also figured out what is the command it is actually calling out to. And also, if you observe here, we could have, see, this is the process that it happened. A Word document was opened. The moment the Word document was opened, it actually started a bunch of other services. See, this actually justifies our, I'll probably stop the capture. Okay, a bunch of other activities are happening, and it, see, the Word document is still running. You will suddenly see something very suspicious. Now it spins a bunch of process, it does a bunch of process. Since the code is showing you PowerShell, this will also has to call a PowerShell process. Now, the moment we see a PowerShell process, let's try to see, go cancel. Let's look for PowerShell. I think we have to probably scroll down a lot to check this. Anybody spotted quickly a power? There we go. So this is also spinning a PowerShell. There we go, there we go, there we go. Sorry, it's too fast. It's too fast. So hold on. So there is a PowerShell here. If I go to properties, see, PowerShell is a process that's spun. PowerShell can be a very legitimate process also. The moment it spins a PowerShell, a process, can you see the same code that we observed in this window matches the same thing? See, this is a PowerShell EGBA that you spotted, EGBA, whatever. The same thing is spotted here. So our assumptions are correct. So both these way of solving the malware yields you the output. You got the domain name and the IP also. You understand how the malware works. You know where it talks to, how it talks to. And you also probably understand the fact that these malwares are talking to the internet to download something and abusing PowerShell. Now let's decode the PowerShell. If you go to your exercise section, right, that I asked you, there's something that I've put it for you. So let's decode it and see what actually happens. Let's go to Google and do a base 64 decode. This is base 64 encoded. If you see those two equal to signs in the end, it's usually base 64 encoding. So we're going to decode the base 62 decoder. Okay. We're probably going to do the base 64 decoder, copy it, paste it here. And once you probably decode, it should decode. Oops. Why is it not working? Should work. Let's see some other base 64 decoder online. Strange. Why is it? Anybody able to decode it? I don't know why it's not decoding. Maybe it's, I think I have some formatting issue maybe. Yeah, I think so. 1 second. Yeah, I think it's some formatting issue. I'm sorry. Should work now. Let's copy it and see again. I just copy paste it just like that. So it should be some formatting issues. Hopefully works. Strange. I don't know why it's not working. Should work. Let's see. I think it's some sort of a formatting issue maybe. It should be fine. I think I've copied everything correctly. I'm not too sure why it's not working. Oh, there you go. There's some formatting issue that we had. So yeah, when you probably copy paste it again here, right? Now this is the encoded format. Now what happens is when the document was opened, this was like an encoded thing and it's a PowerShell, right? When the PowerShell was probably called, it decodes itself and there you will see that it is calling to a domain, domains like HTTP, VR Kerala, XYZ, SuzukiInstallion.com. And that SuzukiInstallion.com is what it's seen. So you can extract a domain by using behavioral analysis like this and also running it and checking it with your fake DNS, and also can do manual analysis and also get the same domain and output. So that's what I actually wanted to show you. There are like 10 different ways of solving a problem. What you guys did was using the tool, since you like Bainer, so we did it. And you can also solve using the fake DNS and this option also. Any questions? Was this interesting? So you end up downloading, you probably end up doing both the malware. Yeah, it's because of the extra space in the code. Yeah, I didn't see that, so my bad. I got this new monitor, so it's wide, it's really wide. So I'm just getting used to it. So that's why. Thanks. Do you guys like this part? Awesome. So you guys like it? Interesting or okay? Enough of probably watching. Let's probably get to business and probably solve our final portion for the day using something called as memory forensics. Okay. Let's do memory forensics next. Okay. Now my Windows job is done. I'm not going to use Windows anymore. Okay. Sorry, I'm not going to use Windows anymore. I'm probably gonna more run on this one. This one can also be closed. Okay, good. I'll minimize it. Sweet. So this is the portion that I wanted to show you, and this is how it's probably done. I'll probably, so you understand, no, what is the process, how the process ID works, and everything works, and so on. Sweet. Now let's do this. I mean, I'm just gonna stop my snapshot so that next time. Sweet. Okay, let's do this. Now let's kill this also. Now let's do something called as memory forensics. Now, what exactly is memory forensics? You'll probably there's a session probably coming in one of the days for you guys. It's going to come up next shortly, like I think a couple of days or days after that. See, whatever we did now, right, was running a malware, obtaining an evidence using tools and a bunch of stuff. Now, memory is the most, the most interesting or the most amazing space that you can probably look for things. It's just brilliant. Okay. Now the Windows in malware terminologies, right? If you probably talk about malware and its terminologies, a malware has to run. A malware can hide. See, it is hiding, right? Here in this context, it was hiding happily and everything. But the malware, even though it has hiding, it has to run at some point of time. Okay. Now, when the malware runs at some point of time and it runs, it will have some evidence of its footprint in the memory. So that is why they usually say, even though the malware fools you when it runs on your computer, the files are encoded and all those things, the best place to look for is probably into the memory. Okay. Now that is what we'll probably try to do here using something called as memory forensics. Okay. Now, this is the most important part we need to understand in memory forensics. I told you the memory, the process story. I told you the locker story, locker space and everything, right? Now, that is what we're going to do. Now, what we have done in this case is, if you go to CD downloads, okay, there's something called as CD memory. Okay, let's go to memory. And there are like two mem dumps. We'll try to do both. We'll, in the interest of time, let's see if we can do both pretty quickly. Okay. Or we'll do one at least. Okay. So what we need to understand is this is the memory dump or a memory capture of the computer. Now I ran the file on Windows, right? We ran the file. We looked at the process. We looked at the network connections and everything, right? Instead of doing it as a live analysis, what we do is we allow the malware to run inside the machine. Okay, we allow the malware to run inside a machine, and once the malware runs inside the machine, we wait for some time and we dump the memory of the entire computer. Okay, we are dumping the memory of the entire machine. Once you dump it, you'll get it in the form of a vmem file, virtual memory file. Okay, now there is a tool called volatility. Okay, now volatility is a Python based tool which will basically walk through the memory image and get you the details. As I mentioned, right, everything in memory is a doubly linked list. Okay, every memory in Windows or in any computer is a doubly linked list. Okay, now in memory, when a process, I showed you there's a process ID, right? Those are sections in each memory. And the process name will have a pointer that points to a doubly linked list, which is actually has the process ID. That in turn will have a list of details and so on. Okay, so we need to convert virtual address to physical address or physical address to virtual address to look into these sections of the memory, which is what we are probably going to do. The tool will do it for us, but I'm explaining you how it happens because it's very, very important to understand the tool. Okay, now let's extract it by using 7z. Go to your Linux machine, press X and type credex memdump.zip. Okay, press enter. There is no password required for this because even if you run it, doesn't make sense for you. Okay, 7z x credex memory dump.zip. So this is what we are probably going to run. Okay, perfect. Now, before running this memory image, you will get a memory image like this. Okay, you'll get a memory image like this. Now we are going to tell this tool called volatility, which is .vol.py, to say, hey, I have a memory image. F is a file saying credex.vm. Okay, .vm. But I don't know which operating system it is. Is it Windows? It is Unix? It's Linux? Is it Windows 7? It is Windows 10? Because each Windows, each Windows version, Windows 10, Windows 8, Windows 7, Windows 6, anything that you take, right? XP, they have a different way of, pointer accessing. Okay. They have a different way of pointer accessing. Okay. You need to know to look for the right places. So if you get a profile, this is actually called as a profile. If you get the profile right, you know where exactly to look into. You'll tell, hey, the tool will know, okay, this is Windows 7. Actually, he mentioned it. So let me take a look at how the Windows 7 is structured. So you need to gather this by using image info. Okay. You need to gather this using image info. Okay. Now I'll tell you how it actually works. Okay. Nobody talks about this also. People just run the tools blindly and they start working. Now, how does this tool actually know that how does the tool actually know that this is Windows 86 or Windows XP? Okay. That is because every file or every operating system in Windows, right? Every file like doc, PDF, image, MP3, WAV file has a magic value. Okay, now everything works by magic value in Windows. Okay, magic value is a number, it's hexadecimal number that basically works, that tells you what is it. There's a value, it says, okay, the operating system understands this as a Word document because it looks at the magic value. Now, similarly, for operating system versions also, there's a magic value. You can actually see the magic value on your own. How? You need to type this command with me. WX, you type and then you type tab. Just type W hex H and then you have a tab. Okay. Now you have the hex editor file. Now hex editor. You want to open the memory image, right? That we actually had. Let's open the memory image. I'll show you how we are looking for the magic value, how this tool looks for that magic value. Okay. So once I open it, I get it in a hex editor. You can probably Google about this later, okay? The different magic values that are basically associated. But usually inside the memory, if a magic value for an operating system is spotted, you will have a series of 8 zeros. Okay, not A0, a pair of 8 zeros will be there. Okay, there will be a pair of 8 zeros followed by a 4B44. You can Google about the other versions. Each version has one number. Some will have 04 in the end, 06 in the end. We need to look for that particular version. Okay. Now, there's a term called KDBG. If that string appears next into this, then that means this number belongs to an operating system, and with this number you can locate which operating system it is. Do you see there's something called as KDBGE, and it says 42 and 77. This section 9002. This means that this is actually a Windows XP machine. Okay, but for Windows 7 it is different, Windows 8 it's different, NT it's different, server it is different. Now this is how the tool volatility also identifies that, okay, this image that we dumped belongs to an XP. So let's apply the set of commands so that we know that we are working on an XP. Similarly, you can search for the other things. This is what the tool basically does. I'm just showing it manually to you. Okay. Similarly, if you take this dump and you can look for a PNG image, if it's stored, if you put a magic value, you can find out if it's a Word document or if it's a PNG just by looking at magic values. This is the power of a hex editor. This is how your operating system internally actually works in identifying if it's a Word document or a PowerPoint, and it designates the application to open these things for you. Okay. Now this is how you identify the magic value. Now, as I mentioned, that I know this is like a Windows XP. So any service pack, anything this out of these two will work for me. Service pack is different. But now, okay, so now we are good, right? Now I'm going to tell, okay, volatility. I know the file, which is actually credex.vmem. And I know the profile. This is called as a profile. Okay. The profile for this is actually Windows XP, right? It's actually Windows XP, SP2 or 3, you can apply probably anything, and it's an x86 processor. Okay. Now I've given you those details correct. Okay. Now what you do is, I know this is the Windows machine. I need to find out what were the list of processes that we observed in the Windows machine, right? Tell me that, give me the list of process that this computer was running when the malware was also running. Okay, and when the image was extracted. So this is as PS list. Now what volatility will do is, it knows in the KDBG where the list of processes is stored. I told you, right? This is also doubly linked list. It will have a pointer. It will reference the pointer and it will give you the output. Now this is the list of process that is probably observed here. Okay. Everybody's clear here so far. Do you guys like it? Is it interesting? This is I love memory forensics. So it's like a movie. It's like a crime thriller movie that keeps going. Like the Anjam Patra movie in Malayalam. So it's very interesting. So do you guys like it? Can we proceed? Any questions? Is it interesting? Boring?
So can you show the profile command?
Oh, you want to see the profile command?
Yeah.
Yeah, sure. Yeah, this is the command.
Okay.
This is one you are asking, right?
Yes.
Okay. Cool. Now this is how you get the list of process. Now here with the list of process, you can probably figure out which was a suspicious process and which was not a suspicious process. I think this takes a little bit of practice. You need to understand what are the list of legitimate process, what happens, so on. But to simplify and speedify the process for you guys, I will probably take a look at this reader.exe, which looks strange. Now, usually you have a process ID, parent process ID. Okay. And this also gives you the start time and this one. And if the process died, then it will give you an exit time. Now, if you see this reader.exe looks suspicious to me, and the process is 1640 and the parent process is 1484. Okay, it's 1484. So I'll probably quickly look at 1484. Let me check what is 1484 here. Explorer.exe. So somebody has opened an application, and that was the parent process which spun a child process called 1640. You can do it for others also, but it'll be a dead end. Okay, this is all legitimate process. You have to Google and see what is a good process, bad process. That's what everybody does. And here in our case, this is our suspicious process suite. Okay, usually what we do is there's one more command called as psx view. Okay, now this is actually coming only from your ps list. There are several other data structures inside a memory. Sorry, there are several other data structures actually in the memory, which mm, which actually gives you the list of processes also. Okay, now this plugin, this command, right, helps you to compare the other data structures so that we can find out if a process is basically hiding or not. Okay, it'll pull in all the data structures, and then it'll probably give you a combined value saying that okay, these are the three things that are actually there, and then based on that, this will probably show you the list of collated process. Okay, now here you will get a yes or a no kind of an answer usually here. Okay, if you get this yes or a true or a false, sorry, a true or a false answer, if it's actually saying false, 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 false for everything, right, that means the process is basically a hidden process. Now those hidden process can never be seen the way that we saw, right, because it lives in the memory. We can't see it the way that we did in the Windows machine. So here this the process that we saw is not a hidden process. Okay, you see there's something false here. This could be a hidden process. It's not a hidden process. It has to be false everywhere. Now here, if you see, this is not a hidden process. So I clearly told you one important fact, right? Now this is the process that we are probably going to inspect. Okay, now two things. I told you two things. Every process will have a process ID and a process name. And didn't I tell you that each process will have a process memory? Every process will have memory for itself so that it can store the data related to its process and also data related to its operations. So can we probably do something interesting here? What can we do here is we will probably dump the memory of that particular process, and if we dump the particular process's memory, we will get the artifacts from that memory. So we'll know if the process is bad, what was it doing, did it dump any files, did it download anything, and so on. But before that, our goal and intention of the entire class is to find out domain names and IP, right? Now, if this process probably spoke to the internet while running, it would have made some internet connections. We need those data so that we can block the domains and IPs. Now, Volatility has a plugin for that also, okay, which is actually called as conscan. Okay, the moment you run it, Volatility will go and look for the doubly linked list that maintains the socket connections. Now, whenever in memory, when the Windows API for socket is called, I showed you, right? Internet open URL A, I showed you, right? When that API is actually called, there is an instance in the memory where an entry is made inside the TCP IP _4 table. When a socket is created, a socket maintains a data structure called as TCP IP _4 or 6 in the memory. Okay, now we are going to ask Volatility to look inside that data structure and tell me what were the list of domains or IPs that were actually run. Now, who's the culprit? The process 1484 has actually made an internet connection to some remote address. Okay, now who is 1484? This is the parent process of our 1640. So this is definitely suspicious. 1484's only child is actually 1640. So when this was started, They started talking to the internet, and then suddenly this process spun, then something was probably going on. So this is basically worth inspecting. But I need to know who spun this process, who created this process, or who triggered this process. For that, volatility also looks into the memory to look for a command called command line. Now, this is a memory linked list that's there that stores any keyboard action or a history of commands that was actually executed in the operating system. I think that's why when you type history, you're able to retrieve the list of commands run on an operating system. If you type this, you will see the list of commands that were actually run by which process also. Volatility basically carves or lists through the doubly linked list, parses the data and presents it to you here. Okay. And if I see, if I'm not wrong, this is the suspicious process. So I think somebody got an email, which could have been a PDF document. In our previous case, it was macro. When you opened a Word document, macro ran. Similarly, PDF has also got JavaScript inside it. Instead of macro, when you open the PDF document, JavaScript scripts can be embedded, which can download URLs, can do a bunch of same logic. But here it's macros and VBA. Here it's probably JavaScript. So we 100% know this 1640 is the big culprit. And this is one that actually triggered it. Now let's go ahead and probably dump the memory of this process. Okay, I'm going to dump the memory. Okay, dump the memory of that suspicious process so that I can get some artifacts or some objects from that which you can probably inspect. Okay, now in order to do this, something called as proc dump. Okay, something called as proc dump. This is a plugin that allows you to tell, hey dude, this is proc, give me the process ID so that I can dump the process. Okay. Now in our case, -p is the process. We are going to dump the process 1640. Okay. And we also have to tell volatility saying that, hey, dude, can you dump it in my current directory? If you don't mind, so you're saying dump directory space dot. Okay. We're just saying that, hey, can you just give me the dump of this particular process? I just want to probably take a look at it, what exactly is actually happening. You press enter, it is dumped. So if you observe, when this actually ran, this spoke to the internet, right? It spoke to an IP, and I think it downloaded an exe and it saved in its memory. Okay, this was probably not physically present inside the machine, because your antivirus will detect it. This is a sneaky way of storing data inside the memory, executing inside the memory and dying inside the memory so that no one suspects you. So we did this. Now let's do one more thing also. Instead of proc, I'm going to say that it's okay. You gave me the process dump. Can you give me the memory dump also? Can you dump the entire memory of this process? So I can run strings against it. I told you strings, right? We can run strings against it and see what are all the strings embedded inside the memory of this process. Okay, instead of proc dump, you're typing memory dump and then pressing enter. It is going to dump the memory to you. Okay, now all this is possible because we know this pointer, this is the process. We know where the pointer is. We are pointing it to the pointer, carving the memory and getting the data dumped back to us. The tool is doing it for you, but we're also understanding how it is done. Okay, sweet. Now we have both these things. We have an executable and we have a dump of a process also. Now let's run strings against this executable. I'm probably going to run less. It will be probably big. Okay, I'm going to run strings against that memory dump. Okay, I'm just going to run strings against the memory dump. Now it says Adobe Reader. It's actually an Adobe Reader. Do you see it's actually used the API, get system Windows directory. It's asking which drive you are in. And it is also launching adobe.exe. And there's a bunch of gibberish strings. It's run this reader. So we are right, 100% right, whatever we observed. And do you see this list of domains it's actually trying to talk to? These are all popular banking domain names. You know why is it looking for these things? It is actually trying to look inside a browser's history to see these were the banks that were actually accessed so that it can steal password from this. This is called as a banking Trojan. Okay, that is why it has got a list of banks with it. It's checking all the bank names to see if the user has accessed anything. Okay, and if he's found it's accessed anything, it'll probably next step, it'll probably go inside the browser memory, and probably it'll start, malware will probably start looking at the history of the browser and see if this guy has got a bank account. They'll send a phishing mail later, or they can probably extract the details of the bank. See, there's a lot of bank domains here. This is the list of banking Trojan. This is the list of banks that this Trojan is looking for. These are probably called as banking Trojans. Okay. Now that is one. You can run the strings against the executable file. Okay. You can run the same strings space against the executable file and see this API. So didn't I tell you? It's basically looking for the current process and it is trying to inject into the process. Didn't I tell you? And these are the things it's probably trying to do. It's loading a cursor, it's looking for icon, it's doing a bunch of interesting stuff. If you probably go through this, you'll know. Like a story, it is basically getting a current process, and then it's actually finding a file. Find file, next file means it's iterating through the list of files. Then it looks for directories, then it's looking for to create a file, then it's terminating a thread, it's writing inside the registry key, it's opening a service, and it's doing a bunch of interesting things. But this malware is an evasive malware. I'll tell you why. Because if this is debugger present means if I put a debugger, right, Win debugger or Oli debugger, the malware will crash. The moment it checks for this is an evasive technique. And tick count is also an evasive technique to see how long this machine has been up. We have been using this machine for 3 hours. But if you use an online machine, right, it'll be spun only for 5 seconds. So it'll get the uptime of the machine to see if it's someone is trying to study them or someone is really genuinely executing it. So that is memory forensics for you. Do we have time still? Do we want to run that last sample or do we have time? So when's the next session, sir?
Shyam,
So do we still have time or we're done?
like if you want, you can continue for a couple of minutes. Like next session is at 3:30.
No, I think it'll take another sample is there. I think it'll take a little time. So
Yeah, maybe then we can stop, Shyam. Is it fine?
yeah, it's fine. It's fine. Okay, I'll just tell them the tricks are the next sample.
Yeah, or
Okay.
maybe like when you return back, maybe you can share the the video.
Yeah, I can share the video. I have the video. So what is the next sample? I'll just quickly tell. So I'll just take 2 minutes. Okay.
Super.
What is the next sample here is to extract. Okay, I'll just clear the screen. The next sample is actually very interesting. This is the memdum sample. Okay. Now you can run a volatility plugin. Okay. I'll just show you the plugin. You can run a volatility plugin, which is actually called as Hive List. Okay. When you run Hive List, it tells you the list of locations. Usually before Windows 8, password is split and stored in SAM and in system. Okay. Password is basically stored in SAM and system. Okay. Usually the NTLM hash, the passwords in Windows for local accounts before 7, I think it's until 7, were stored into an algorithm which was split and stored into SAM one portion and system another portion. Okay, you can use a volatility plugin to extract. This is your virtual memory. This is your physical memory. You're telling volatility saying that go inside system in this memory location and go inside SAM in this memory location and get me the NTLM hash dump. Once you get it, it'll probably look like this. Okay, it'll look like this. I put it in the exercise. Once you probably look at it, it'll look like this. You can probably go to this crack station website. Okay. Now, how the password combination basically works is you have a username. Your password is basically split into two. Okay, it's split into two different types of hashes, and it's actually split so that once you probably combine it, there's a hashing algorithm. You have to rehash it and do it, but there are tools online. Now, if I probably copy this that I extracted, I'm not a robot for sure. So, oh, sorry. If you probably copy this section, sorry. You probably copy this section that once you obtain, you can probably see the password. Okay. Now you can use memory forensics to extract password also. And if the person was really stupid enough, okay, really stupid enough to run it, right? I showed you this consoles command, right? If the person was really stupid enough to change this and probably do it, okay, then there's no consoles here. When you run it, you can see the password changing command also there. But the other way is probably to take this command. This is the hash. You can go to this crash station site, keep doing it. For every user account, the user account is never hashed. You can see the password here. This is to retrieve password from a memory dump. This is the guest username. That's the password. So still now Windows 10, it's all changed now. It's not there that way. So that is how you do reversing. We've not done IDA Pro. Assembly level reversing is very hard. It's like very harsh to do it in 3 hours. But this is your basics reverse engineering for memory and malware kind of forensics. For a doc file, you can do the same for a PDF file. You can do the same for exe file. And also we saw about behavioral analysis of files, static analysis, and anomaly based detection using patterns along with threat hunting. So I think that's all I have. I hope it was a big use of your time. I hope I didn't waste none of your time, and I'm happy for any questions or any comments. Did you guys like it? So based on the pattern identified, is it possible to predict similar patterns? Yes. That is where you use machine learning, Visaggio. So you can probably use machine learning to do string similarity or instruction similarity or pattern similarity. And if you probably use a bag of words or a bag of models, you'll see an intersection between two samples. And then if you probably run it through, you can find a lot of string patterns and other patterns and use it in machine learning. So see, every malware is somewhere or the other interconnected, because only 1% of malware or 2% of the malware is written by original hackers. The rest are all, it's like Stack Overflow. People reuse it. It's sold in the internet. They make use of it. So nowadays malware use different patterns. How to find? You have to do this combination of tricks that I taught you. Okay, manual, tool, psychological analysis, open source hunting, and memory forensics. These are the only patterns that you probably have. Use probably machine learning, string similarity. You have to use a combination of these methods to do this, to find different patterns. It's a very challenging field. There is no particular style of doing things. There's a very different way of doing things. Some people like automating it. I like doing it this way because I can use it for my machine learning work also. So what else? What other questions you have? I'm less scared to go into this field. I live in this field. I'm very cautious about everything that I open or click. I become an insanely paranoid person off late. So, but it's a very lovely field if you probably want to work on. It's amazing. It never ceases to amaze me. It's got a lot of, it's endless possibilities. It's amazing. I just love doing it. You should probably, now you probably read the guides or tutorials, videos in YouTube. You'll probably able to understand because we've covered a lot of interesting basics and most of the things that books don't talk, at least. Awesome. Any other questions? I can share a bunch of, you can read a book called as Practical Malware Analysis. I think I don't have the book. I probably put the book back. There are a lot of YouTube tutorials. You just Google about it, you'll find tons. And there's somebody called Malware Unicorn. So that person is also pretty good. There are books, a lot of books called as Memory Forensics, several books, Practical Malware Analysis. There's some interesting courses in Udemy also, Basics of Static and Dynamic. You can probably take a look at it. So now it'll make a lot of sense for you now when you take a look at those courses. Yeah, I can. Yeah, Sita, you can probably reach out to me. I'll not be available for this week, at least. Next week, I'll probably be there. You can add me in LinkedIn. I know it's, I'm sorry, this is little boasting thing, okay? But still, if you want to reach out to me, just Google my, I'm just put in the chat. Just Google my name as Sundar Ramaswami. You'll find me. Just type my name like this in Google and you'll find all about me. Okay. You can add me in LinkedIn, reach out to me. You can, I prefer LinkedIn. Emails, I'm very lazy to write. So, okay, if you want to reach out to my email, the batmailbox@gmail.com is my email ID. So you can write to me there. Can you give a short brief about static comparing with dynamic analysis? Interesting. Will you take net session on network forensics? I didn't have time. I have packet capture analysis. I also teach you how to do threat hunting, dissecting a PCAP. That's also part of the session, but we don't have time to cover all this in 3 hours. So I can take a session on network forensics also. Taking a PCAP, carving evidences out of a PCAP, saving PCAP, and doing a bunch of pattern hunting using PCAP. Yeah, I do. So can you give a brief intro about static analysis? See, static analysis is basically not running the file. So there are no chances of your system getting infected. You're basically looking inside the file to see what exactly is happening without running it. Dynamic or behavior is running the file, carving out the process, process ID, process name, and bunch of behavioral attributes. You'll know how the file will behave. Static, you will figure out how it could behave without even running. It's an assumption, but it's a solid proof. A good mix of both, it needs to be done in order to be an effective malware analyst. But always run your static analysis first to find the clues. Don't exhaust your effort in running a file, because when you probably run a file, it takes a lot of your time and resource and everything. So that's the most important thing to do probably when you, run a behavior analysis. You need probably to do both so that you kind of stay safe. Okay, zero-day malware perspective. This question is interesting. Somebody will ask this question always. So, see, zero-day malware perspective, you have to do combination of everything, right? Because zero-day, you don't even know what that sample is. It's like a sample in the wild. So you run static analysis, see if you have patterns. Sometimes executed, do memory forensics. Is the smartest way of doing for zero-day. Memory forensics is the best way to do for a zero-day perspective. Rather than static or dynamic. That's my take. But memory forensics is very time consuming. You need to look into the right places. You need to carve out. This is easy stuff that I told you. There are a lot of complex stuff. You have to look into the IAT tables, atom bomb tables. There are a bunch of other tables that you need to look. Rootkits are very, very difficult to spot. Only memory forensics will help you to do rootkits. Not these malware analysis. Rootkits are very hard because they mess up with the system tables and these data also. Do you work on Android malwares? That's my goal for 2021. I'm studying on Android malwares. I'm working actively on it, but it's a different ball game, different operating system. I'm not as comfortable as Windows with Android, so I need to learn a bit of Android malwares. So, any other questions before we wrap up? I hope you guys loved it. I hope it was not a waste of your time. I know it's like a good 4 hours. So thank you so much for patiently sitting with me and interacting with me, and I loved it. And if you have any feedback, please give feedback, good, bad, ugly feedback. Saying never ever take a class in your life, I'm also okay with it. I'll improve on my stuff. So thank you, Vinod sir, and the university for this wonderful opportunity. Always a pleasure doing it for Vinod sir. And always a pleasure when I do each of these sessions. I learn a lot each time when I do something. So thank you.
Thank you, sir. Thank you so much for your words of wisdom and the hands-on learning experience. We learned a lot from you. it will be great pleasure for us to listen to you again in our future events. Now, may I invite Professor Vinod, Department of Computer Applications, CUSAT, to conclude the session and present the certificate as a token of our love and gratitude.
Thank you, Shyam, for a wonderful session on malware reverse engineering. It is always great to hear you, and it's a long association that we have. And I would say, by stealing your word, an awesome lecture, and it was really great. And I know that you're not well, but still you stood, you assured that you would be coming for this session. I hope that you come up back with in 1 week, and let's discuss for future. And for the participants, we would be sharing a feedback in your individual emails by evening. So we will be having the next session, the first international talk by Dr. Visaggio from University of Sannio, Italy, where he would be talking about the generative adversarial attacks on malware detectors. So which would start at 3:30 p.m. because Italian time, it's too early to start now. So he will reach university by 11 a.m. So that is the time. So we start at 3:30 p.m. Sharply. So thank you, Shyam, on behalf of the entire faculty members of Department of Computer Application, for sharing your valuable thoughts. It was really impressive, and you are always great. Thank you. Thank you, sir.
Thank you, sir. Thank you so much, sir.
Right, thank you.
Thank you.
Take rest, Shyam. Take rest.
Yes, sir. Thank you. Thank you, sir.
Bye-bye.
See you. Bye.
Okay. Can you see my screen now?
Yes, yes, yes.
Great. Okay, well, good morning all. And today I will talk about the generative adversarial attacks to malware detection, which are attacks produced by artificial intelligence. And the purposes of these kinds of attack are to produce new malware that is recognized as goodware by malware detectors by using deep learning engine. This is the today agenda. As first, we will have an overview about the achievements and limitation of machine learning as it was used for building malware detectors. Then I will talk about our experience in using machine learning for detecting malware, in order to highlight some of the characteristics and, of course, limitation of this technology, malware detection. Then we will see which are adversarial attacks to malware detectors. And finally, I will talk you about our experiment on generative adversarial network. And so we will talk about the conclusions and we try to understand which are the next steps that we have to do in order to successfully face the problem of adversarial attacks to malware detection. Well, as you know, I guess, machine learning has been used largely for building malware detectors. But our question is now, to which extent is machine learning effective for building malware detectors? The answer is not easy and is not straightforward as one can guess it. Especially because we can see some successes of machine learning, but we know that a lot of time machine learning also fails to identify malware. First of all, the bare facts in numbers about the malware universe. Of course, you have to consider that these numbers are just estimates. So this is not the exact picture of the malware universe, but this is a good approximation. So nowadays, we have 200,000 malware a day. This is the daily production of malware. It's really huge number. And this daily production entails about 80 million new malware a year. 80 million new malware. If we add new malware to old malware, we obtain around 700 million malware going around the web and the networks in general. And this is really a huge volume of numbers. And this is the real problem that we have. So I want to start from the first conclusion of my talk. The first conclusion is that our current technology is very weak, is really not appropriate to face these volumes of malware. And this is the first point. The second point is that if we have such a volume of malware, we should face this problem of malware detection with automatic approaches. So this is the very point of our talk today. And this is the very point, the very problem that we have to solve in our present. How to recognize automatically all these volumes, the overall number of malware going in the wild. We have to consider too that especially great organizations are hit by targeted malware. So we have malware that is created just for hitting some specific organizations. And this is a very huge problem. We have to add to this scenario also the great proliferation of zero-day attacks. As you know, in the darknets, we have a lot of markets where people sell 0 days. Nowadays, we have a very important economy about 0 days, but we have another problem, the conceived cyber arsenals. Cyber arsenals are basically malware and exploits that are developed by organizations, sometimes governative organizations, and of course, usually they are preserved and they are not public, but it can happen that these cyber arsenals can be discovered by adversaries or criminal groups and these arsenals are used by criminal organizations. Why we use machine learning in malware analysis? Because basically when we do malware analysis, we have two problems to face. The first problem is the classification. So we need to understand that a software is malicious or not. This is the first point. The second point is to identify the variants of malware. Variants of malware are malware that is obtained by very little changes to existing malware. But those little changes are a great problem for the identification of malware, for the detection of malware, because these little changes fool very well the malware detectors. So we have, we use machine learning for classifying malware, for detecting malware, but also for clustering malware, that is to put together malware with similar characteristics. Another point is that we have a lot of, we are interested in a lot of characteristics because we want to know the static features of malware. We want to know how many files the malware is formed by. We want to know which are the evasion techniques the malware uses, and so on. Till now, which are the features that we extract from malware for machine learning classification? Basically, we have a lot of features, really a lot. And as we can tell later, this huge number of features entails another problem, which is the so-called curse of dimensionality. That means that we have to consider hundreds of features in order to classify malware. In this slide, you can see just the main classes of features that are used, and you have to consider that each of these classes, contains a lot of features. So we have a lot of Windows API and system calls. We have a lot of n-grams, and of course, this causes a combinatorial problem. We have a lot of strings to take into account. We have a lot of opcodes and so on. So this is one of the problems. Another problem is that we have a lot of studies in machine learning applied to malware detection. But as you can see here, our papers are very different. So we have a strong focus on certain techniques, on certain classification methods, but we have very few works on other classification methods. We have data sets that vary a lot in terms of size, as you can see here. So, and of course, we have also accuracy values that are very different in literature. So it's very difficult to have some very strong conclusions in literature, very strong evidence that can allow us to say, okay, if I want to catch this malware, I have to use this machine learning method. In this very interesting paper, you can see a good overview of all the machine learning techniques used in literature and which are the main results and which are the main evidence. And as I told you, the conclusion that I can have from the current literature that we cannot have evidence at all, because evidence is very varying according to different scenarios of application. So we have really a great problem. And we have great problems for many reasons. First of all, we have two important biases when we use machine learning for malware detection. The first is the spatial bias, which consists of unrealistic assumptions about the ratio of goodware and malware in the data. So basically, we don't know in advance how many malwares are in the wild. Then we have the temporal bias, because as you have seen, a lot of malware raise every day. So malware changes continuously. And of course, this makes our dataset, our training sets, not representative of the real malware population. We have another problem, the so-called base rate fallacy. It was demonstrated 20 years ago, so it's very known in the community, which means that the true positive rate and the false positive rates are misleading in intrusion detection. Because we have a very relevant class imbalance, because most traffic is banning. So actually, we have not the real ratios of malware in the overall populations of software we use. And there is a very interesting and recent experimental verification that in practice, these biases cause a decrease of performance about 50% in malware detection. So these are very serious problems to face. But we have also huge problems regarding data sets. And this is a very great problem when we do research in malware analysis and malware detection or malware classification. First of all, our datasets become quickly obsolete. They are incomplete, they are imbalanced. For instance, we have a lot of malware for Windows, but we have not so many malwares for Mac OS. We have a lot of malware for Android, but we have few malwares for iOS. We have a lot of malware for workstations, but we have a few malware for industrial systems. So we have another problem now. To which extent we can trust the dataset that we use, because we use datasets that are built by other researchers, and these researchers usually label the dataset. So they tell you, okay, this malware is called like that, and this malware belongs to this family, and this malware has these evasion techniques. But can we really trust this classification? The last question is, how much does the dataset polarize the research strategy and goals? Because what I mean by this question, I mean that, of course, you can do your research on the dataset you have, but your datasets pose you some constraints about what you can investigate with that dataset. So our results are limited also by this kind of constraints. Now, I wanted to tell you some of our experience about machine learning. Of course, these are just 3 works in order to highlight which are the problems with machine learning in malware detection. So in this work, what we made was to investigate, was to compare different machine learning techniques on the same training dataset. So what we, and test dataset. So what we wanted to do, what we wanted to understand was the impact of using different techniques of machine learning. So the main results are summarized by these 4 figures. And you can see that the blue points represent the malware dataset, and the red points represent the banning dataset. And of course, your detector is good when the 2 populations of points are very well separated. As you can see here, the 4 techniques work in a very different way. So here you have the best technique, but here you have here and here. So the first 2 techniques are not that well. So which are the conclusions here? The conclusion here is that machine learning can have very different levels of performance according to the different techniques of machine learning you use. And here we have a confirmation of this. Here we study Android malware with the 2 machine learning techniques. The first one uses as features the hidden marker models, and the second one uses as features the structural entropy of software. And also here you can see a very huge difference, among the different malware, the different machine techniques used. Finally, we demonstrated here how formal methods can be successful in recognizing ransomware. I don't want to go in depth in the method we used, and this is not machine learning, this is formal methods. And the very interesting point here is that formal methods can reach a very high level of precision. And the very interesting conclusion is that these very high levels of precision can be reached also when we change the malware. As you can see here, we maintain 99% of precision in our detector, but this is formal method. Formal method means that you can represent exactly the behavior of your malware, and you can define exactly the rules that your malware must observe in order to be defined malware. And this is the main limitation of this technique. Finally, we demonstrated how malware detectors behave when they meet malware that they have never seen before. In this case, we have the problem of concept drift. This problem, known in literature, happens when new variants of a known malware deteriorate the performances of a classifier over time. So we wanted to measure the resilience of a classifier when faces an unknown malware. We measure the resilience in terms of decay of accuracy when the same detector works with known malware, so variants of known families, and when detectors work with variants of unknown families. The results were really terrific. The number here that you can see is the loss of accuracy. And you can see that we can reach loss of accuracy of 60% in the ROS cases. So what we can conclude is that machine learning is a really good technique when you know the malware you want to classify, and that the performances vary a lot by changing the training set, the testing set, and the algorithm that you use. So it's really a tricky solution for malware detection. And now let's talk about these adversarial attacks that go to make all the scenario rust. What is a generative adversarial network? A generative adversarial network that we call the GAN from here on is a tool that produces adversarial samples by using the adversarial machine learning. The adversarial machine learning is a technique that defines sample that can fool a detector. What does it mean? You know here two images. It's a bare human eye. These two images are identical. This is a street signal. And you can see here that we have to, they send the same image. Actually, they are not the same image. The image on the left is the original image. The image on the right is the image produced by a GAN. The GAN basically changes some pixels in this image. And when these pixels are changed, the automatic recognition of the signal is completely fooled. So the engine cannot recognize the adversarial sample. But the engine can recognize the genuine sample. So this is the problem of adversarial sample. So our question now is how and how much GANs are able to degrade the performance of malware detectors based on machine learning. So first of all, we observed a move from machine learning to deep learning, which are the bottlenecks of machine learning. First of all, the high time required to learn when the number of or the size of features is very wide, and also when the number of samples is large. But if we decrease the number of features, this could shorten the learning time, but this could produce a decay of accuracy. We have also other problems in machine learning because we can have problems related to the curse of dimensionality. We have problems caused by the computational effort of the machine, and we need a strong knowledge of the domain. So deep neural networks was welcomed as a solution to all these problems, because these are particular kind of machine learning algorithm leveraging several deep layers of networks. Furthermore, deep learning can solve the problem of the representation, because with deep learning, we build very simple features to model a very complex concept. So traditionally, researchers build a single deep learning model with the entire data set. But the single deep learning model could not manage the huge complexity of malware data distributions, because malware has sample subspaces which are related to families and types of malware, and each subspaces has its own unique data distribution. So we have to measure the drawbacks in building a single deep learning model when we deal with the malware analysis, because we have a complex data distribution and we need a very quick scalability. Then training deep learning models on very large data sets is a computationally expensive process. So for solving all these problems, the solution is to use ensemble-based deep learning models for malware detection. Two kinds of neural networks are used in malware detection, mainly convolutional neural networks, which deploy convolution operations on hidden layers, and parameters reduction. CNN can extract local information from grid-like input data, and CNN have already shown very interesting results in other fields like computer vision or image classification. Then we have recurrent neural networks that usually are adopted for processing sequential input data with variable length. Usually this kind of technology is associated with LSTM and gated recurring unit in order to avoid the exploding gradients of recurrent neural networks. So the GANs basically are generative model. This means that the GAN is aimed at producing new models for detectors. And we can distinguish usually in a GAN architecture two components. The first one is the generator. The generator creates artificial samples, and we have a discriminator as a second component. The discriminator acts as an adversary to determine if the generated sample are real or fake. And usually this kind of discrimination is obtained by solving an optimization function, like the general one form that is shown in the slide. So we have a kind of competition between the generators and the discriminators, where the generators try to produce models that cannot be discriminated by the discriminators. Unfortunately, machine learning and deep learning engine can be fooled by adversarial samples. So what you have is that your GAN produces samples that cannot be recognized as malware by engine based on machine learning and deep learning. GAN works on two approaches. The first approach requires the access to gradients of data. In this type of GANs, we have the introduction of perturbations in the data, and this is a white box approach. This is the most rare case. The most frequent case is the black box approach, when we have access to prediction function. And in this case, which is the usual case for malware detection, we can have access to the results of the detectors that we want to attack. In literature, we have different solutions for these two kinds of malware, of GANs, sorry, not applied to malware detection. So for instance, we have the fast gradient sign method, and this uses the gradient of a model to find adversarial examples. And they consist in optimizing a specific model that takes into account the adversarial samples and the data set that we put within the discriminator. In my slides, I give you some models. All these models have the same approach. So basically, they consist of optimizing specific functions. So we can skip this part because it's just different formulas that these authors defined, but I wanted to give you this in the slides in order to have some references for your eventually for study. What is interesting is how adversarial attacks were applied to malware detectors. So we have to consider that the first difference between image and malware is that if you change a few pixels in your image basically can be yet recognized as an image. But if you change some bits in a malware, the malware, of course, can be broken. And for instance, it cannot run anymore, or it cannot be recognized as a legal file, because the operating system recognizes it as a corrupted file. So the point when you change the malware is that the malware must remain uncorrupted. So you cannot change arbitrarily a malware. Different solutions have been found in literature for doing that. We can find some authors who propose adding padding bytes, so we can call it adversarial noise at the end of the file, beyond the portable executable boundaries. But of course, this is dangerous, because everything I put at the end of a portable executable can be easily detected. Another solution is to inject adversarial noise in unused portable executable region that is not mapped in memory. This is very difficult to achieve because, of course, you have to put your stuff in regions that you cannot govern, so you couldn't have enough space, for instance. Then you can add some noise to malware, extracting specific features, like, for instance, imports. But also in this case, this is a very delicate operation, because you can corrupt the working of the file. One of the main examples of a gun applied to malware detectors is Malgan. The GAN. So the idea is that if the program calls a specific API, the dimension related to that API is set to 1, otherwise it is set to 0. So the probability distribution of adversarial samples from Malgan is determined by weights of the generator. So what this does is to just add API calls which do not appear in the genuine version of malware. So this is the main limitation of this technique, that you can just add API calls. This is the architecture of Malgan. So as you can see here, you have the malware and you have the noise. So the generator, what the generation does is to add this noise that basically has a uniform distribution in the range 0, 1. And this noise is added to the malware. Then the final generated adversarial example is expressed as an OR combination between the original malware and these noises. And this means that what you give to the discriminator is the original malware with a set of APIs added to the malware. And I recall here, this is the main limitation. I want to recall here also that what is missing in the current literature of GAN against malware detector is that we have only theoretical models. We don't have till now actual malware produced, built by a gang. So we don't know till now how to build a malware with the features determined by a gang. Okay. Well, of course, we have done some experimentation about generative adversarial networks applied to malware detector in order to understand if this technique is successful or not. Our experimentation was published in a book named Malware Analysis Using Artificial Intelligence, published by Springer. And our paper is entitled A Comparative Study of Adversarial Attacks to Malware Detectors Based on Deep Learning. So, our case study involved multiple guns. So we built couples of generators and discriminators run in parallel in order to realize a multi-staged black box attack. So we adopted the realistic hypothesis that an attacker knows very little about the system he wants to attack. So we are in the case of a black box attack, and the attacker could set up a kind of brute force attack, deploying a pool of generators built for interacting with the malware detectors that we want to attack. The only knowledge, for this reason, the only knowledge that the attacker has is the results of the malware detector he wants or she wants to attack. The attacker trains several generators working over different groups of features, and this allows us to refine continuously the generation of artificial adversarial samples. The training stage is performed without interacting with the real target. The attacker starts with a very little interaction with its victim, and this interaction is aimed at obtaining the results of the classification of GANs produced malware. So we train 10 parallel GANs simultaneously. We had a fully connected feed-forward network architecture where we built 4 discriminators, while for generators we adopted a convolutional layer architecture. We called this approach the patience attackers approach, because the attackers needs a lot of time in order to conclude the attack. We consider only surface features extraction from binary files. So we included only features that can be extracted with static analysis from our dataset. We trained, validated, and tested the discriminator models for malware detection by adopting all the same samples extracted from the Ember dataset, which is a very known dataset, largely used in literature, and contains 1 million of applications targeting Windows operating systems. We selected the first 10 discriminators that obtained the best accuracy in the detection task. And we use only these discriminators. And we trained 10 generators for the corresponding trained detectors. For training the generators, we adopted a descendant gradient based strategy, and we adopted the maximum mean discrepancy as distance function for evaluating samples distribution similarity during the training process. This is the architecture of our case study. As a discriminator network model, we adopted a fully connected multi-layered feed-forward neural network as the base architecture. All the training models differ in input layer size. The basic model adopted for each discriminator of our pool includes 5 hidden, dense, and fully connected layers characterized by decreasing size. For each discriminator, the input size was variable. The maximum size of the input layer was set to 2,351. We adopted the EDEM algorithm as optimization function and the binary cross entropy as loss function. Finally, as an activation function, we adopted the ReLU that allowed to alleviate vanishing gradient issues and is faster when compared with other nonlinear activation functions. We performed all the training cycles for 250 epochs with batch size set to 64. We adopted different learning rates varying in the range 0.01, 0.5. Finally, all the discriminators models could converge to an accuracy greater than 80% and a false positive rate less than 1%. The performance metric values were cross-validated over the validation and test sets. All the experiments were repeated 5 times, and average values obtained in these experiments were considered as the values for the final hyperparameters for tuning the networks. Now the generator network model was represented by a convolutional neural network trained on a sample fraction extracted by the Amber dataset, as I told before. We trained generators until all of them reached at least an accuracy rate greater than 98%. 2 main constraints we had to respect. We have to preserve the functionality of the malware, and we have to preserve the feature probability distribution invariance. Numbers adopted for manipulating genuine inputs have the same dimensions of the input according to the number of features that are considered in each couple of generator discriminator. Each generator was trained for 500 epochs with a learning rate set to 0.05. Of course, in our study, we followed the axis of the adversarial falsification and iterative attack. For the first dimension, we were interested in training the generators that could cause a decrease of precision, of accuracy in the malware detection, so in the discriminators. This is the overall dataset. So we used the 900,000 training samples, 200,000 test samples, and we use the raw features that you can see here in the slides. Of course, these raw features were selected based on the current literature on malware analysis. And these are the results. Well, in the results, we basically compared the accuracy we obtain without adversarial examples, and you can see it in the test 1 column here in the slide. Then the accuracy obtained including adversarial example trained over the training set adopted by the discriminator, And in test 3, we computed the accuracy obtained, including adversarial samples trained over a different training set from the one adopted by the discriminators. So here you can see how large is the decay. So we go from 90–80% without adversarial samples up to 57% in test 2, and we obtain also 73% in test 3. So we can say that GAN has really destructive power for malware detectors. Here you can see evasion rate, and the evasion rate measure basically the false negatives, the ratio of false negative to real negatives with adversarial samples. And we can see how huge is the evasion rate with adversarial samples. We talk about more than 30% evasion rate, which is evasion rate for, of course, the malware detection, the detectors, sorry. In these graphs, we summarize basically the information that we have, and as you know, sometimes image tells us, an image tells us much more than the bare number. And here we can see by our eyes how huge was the decay of malware detectors when we use GAN. And it's really huge differences. And here you can also have the trends of different discriminators. And you can see how much the decay of accuracy produced. It's really an important point. So basically, these are my conclusions about GANs. Adversarial perturbations can easily fool deep neural networks in the testing deploying stage, exploiting blind spots in the machine learning engine. GANs are able to generate a new instance of a malware family without knowing an explicit model of the initial distribution of the data. So GANs are very dangerous because attackers have malware detectors. So attackers have malware detectors, and attackers have very huge malware dataset that they can use in order to fool deep learning malware detectors. Of course, we miss the step in which we build the malware which have the feature produced by the GANs. Actually, frankly speaking, I'm doing this now in my laboratory. So now we have developed a tool that is able to change a malware introducing the features produced by the GAN. Why we are doing this? We are doing this because we want to study how to use GAN for defending ourselves, for making more robust and more resilient our malware detectors. So I'm done with my presentation. I hope to be in the schedule, and of course I will be very happy to answer to your question if any, or if you have some observation on or some curiosity about this talk. Thank you very much.
If there are some questions, maybe we can, yeah.
Any questions from audience?
I see some. I can see some questions in the chat. I can answer these questions if you want.
Yeah, Professor Aaron, there is one question in the chat window. Am I audible to you?
Yeah.
Yeah.
Yes, you are.
So they say that could you please mention the feasibility aspect in the implementation of GAN in order to build robust ML models?
Yes, of course. Well, I think that GAN can be used for producing malware, and we can apply this malware produced by GAN to machine learning based malware detectors in order to understand which features and which algorithm can be used for recognize the GAN's produce malware. So our next step, our next purpose is to recognize the malware produced by GAN, because I can bet on it, the next malware that we see will be produced completely by GAN. So we need this kind of research, we need this kind of technology.
There is another question. I would like to, did you try this for Android platform?
No, unfortunately not. And this is for sure a really good idea. And yes, this can be also a very interesting research strain to explore. But this is a very good question too, because Android platforms is very widespread, and a lot of malware on Android platforms. We have a lot of malware for Android platforms, so it's urgent to have also some research in this direction. So yes, this is a very interesting suggestion.
So another one is, could your data set be used for building ML models? So you have already answered this question. So the malware produced by generators, how malicious are they is the question. Like, has the generator produced any malware that is not seen existing from family or distribution? So they want to ask, the GAN generated malware, is it like a new malware not falling under any family?
Exactly it is. This is another point, because the generator actually produces new malware, and this is a really good point. The generator produces new malware. So this technology will increase also the number of malwares in the wild. And I think that in the next few years, we can see different hundreds of millions of new malware produced in 1 year. So we have to face also this new scenario. So we have to understand that the evolution of malware universe is going in this direction. Artificial intelligence engines to generate very high volumes of new malware that are feed in the wild. So absolutely, you're right. Absolutely.
So we can take one last questions. The question is like, what about malware released in 0 day? And there is another question: how we can effectively choose real and fake data for training?
Well, 0 days is now a very great problem. Actually, I don't know how to face this. I think that technology that is able to mining these forums where 0 days are discussed or 0 days are bought or sold, because actually 0 days is a very big problem, and is doing a lot of damages already. And this is because it's a marketplace, so a lot of people want the money that they can earn with 0 days, and a lot of people looks for 0 days. So it's really a huge problem. It can be solved, in my opinion, only with intelligence and only with miners in the forum.
So thank you, Professor Aaron. I would request participants to kindly drop in the mail to Professor Aaron if you have further discussion, because we are already, the time is already up. Yeah.
Thank you, sir, for such an informative session on adversarial attack to malware detectors. Now, may we invite Professor Vinod, Department of Computer Applications, CUSAT, to conclude the session and present a certificate as a token of our love and gratitude.
So once again, thank you, Professor Aaron, for your wonderful lecture on adversarial attacks on malware detector. Um, uh, it has been a great collaboration with you, and we both are actually working together on a few projects on malware detection. And it's always nice to hear to you, and especially the malware detectors that are fooling that the malware that are fooling the detectors by the generation of new adversarial examples using the evasion techniques using GANs are a big problem to the malware researchers. So you gave us a great insight through your research, and definitely there are certain open issues that you have discussed, which can be pondered by the future researchers to work on. So thank you once again from the entire faculty members from Department of Computer Applications from Cochin University of Science and Technology. A small token of appreciation in the form of a digital certificate might be visible to you. It will reach to you soon. So thanks for accepting our invitation. I know you are a very busy person. You had a meeting today. You canceled just for us. Thank you so much, and looking for further for your collaboration. Thank you. Thank you so much.
Thank you a lot. I'm very honored for this recognition, and for being here in this really interesting and exciting event. My congratulations to you for for the organization of this workshop. It's really
Am I audible? Am I audible? Am I audible? Can you hear me?